有纯数学与应用的，甚至有经济管理方面的一些学生加入我们这个大家庭。
There is a joint program between BIMSA and the University of Chinese Academy of Sciences to accept PhD students. I will start to supervise 2 students from there.
I think the biggest obstacle for women in science in general are people who want to protect them or protect us. I don't need to be protected. That's the worst part, because that's limit my abilities to go further.
经常连做梦呢，然后都是在考虑这些问题。有时候做梦呢，然后就感觉好像是找到了思路，然后半夜就爬起来，然后去验证。就是如果你做梦的时候还没有梦见你在做的东西的话，那估计论文呢还是暂时写不出来的。
我所遇到的这个挑战呢，就是说，我需要找到一条属于我自己的这个路线去做科研。
直到2023年5月，研究院基金累计的引进了科研人员150名，并且初步的组建了量子信息跟量子计算、区块链跟密码学、计算数学、数字经济、统计学、数学物理、代数突破跟应用、生物信息、分析、控制论、数论、代数几何、广义相对论、弦理论、量子场论跟核子系统、概率论、表示论、微分几何，一共17个不同的方向的科研团队。
我们热诚欢迎世界各地热爱数学的科学家加入北京雁西湖应用数学研究院，
与我们进行深入的学术交流，让我们一同去探讨科学最美妙的地方，
为我们中国、为世界的数学事业贡献我们的力量。
数学是很有意义的一个学问，我们解决一个好像表面上一个简单的问题，但是可能影响到很多其他的学问上。
应用数学是要从应用以及技术角度看，以应用场景为导向的数学研究。
我们是从事应用研究，就是要解决实际问题，
而这个实际问题一定来自于社会经济发展的重大需求。
陈市长大概3年前，邀请我到他的办公厅里边交流。他期望我办一个以基础数学来发展应用数学的一个研究院，期望这个研究院能够带动中国的基础科学的发展。
我们有75%的应用数学，25%的基础数学，其中想的是把基础数学和应用数学真正的结合起来，然后起到一些引领的作用。
所以我们一开始就重视了怎么引进人才。
我是2019年从新加坡国立大学回国的嘛，大数据呢、人工智能应用的，其实在欧美已经有非常红火的，但是中国的情况呢，几乎是学科空白。我也大量的组织了很多活动，跟同行怎么来把这个空白的领域呢，给它建设起来。
我一直认为教学是第一重要的，因为我们要培养人才。我们选的学生呢，都知道要充分能够享受雁西湖的资源，他们也对雁西湖非常的渴望，非常期待。
因为我们的年轻人这个水平很高，也因此能够吸引到世界上有名的大师。
When I was younger, math brought me joy because I was just naturally good at it. But when you study enough math, you learn that math is really hard. And so maybe some of the joy disappears and is replaced by curiosity and is replaced by a sense of challenge and accomplishment.
具体到我们这个并不萨这个地方，有我们也自己的特色，我们能够跟来自世界很多国家的学者，来自不同的学科领域的学者，
能够做到一些跨学科的深度的交流。
所以我们决定了明年办一次国际基础科学大会。
这个大会是很难得的一个机会，因为这是一个顶级的盛会，然后参会的嘉宾级别也很高，这种诺奖、菲尔兹奖、图灵奖3大奖，包括国际大奖的这个嘉宾数十位。
I think that during this conference, that many distinguished scientists will come here. They will invite us and say, we want also to come to BIMSA.
I hope all the people who come to ICBS have a good experience and appreciate the effort that's gone into organizing this conference.
我们现在跟各科大、跟百行有联合培养的学生，这些学生呢来自不同的领域，有纯数学与应用的，甚至有经济管理方面的一些学生加入我们这个大家庭。
There is a joint program between BIMSA and the University of Chinese Academy of Sciences to accept PhD students. I will start to supervise few students from there.
I think the biggest obstacle for women in science in general are people who want to protect them or protect us. I don't need to be protected. That's the worst part, because that's limit my abilities to go further.
经常连做梦呢，然后都是在考虑这些问题。有时候做梦呢，然后就感觉好像是找到了思路，然后半夜就爬起来，然后去验证。就是如果你做梦的时候还没有梦见你在做的东西的话，那估计论文呢还是暂时写不出来的。
我所遇到的这个挑战呢，就是说，我需要找到一条属于我自己的这个路线去做科研。
直到2023年5月，研究院基金累计的引进了科研人员150名，并且初步的组建了量子信息跟量子计算、区块链跟密码学、计算数学、数字经济、统计学、数学物理、代数突破跟应用、生物信息、分析、控制论、数论、代数几何、广义相对论、弦理论、量子场论跟核子系统、概率论、表示论、微分几何，一共17个不同的方向的科研团队。
我们热诚欢迎世界各地热爱数学的科学家加入北京雁西湖应用数学研究院，
与我们进行深入的学术交流，让我们一同去探讨科学最美妙的地方，
为我们中国、为世界的数学事业贡献我们的力量。
数学是很有意义的一个学问，我们解决一个好像表面上一个简单的问题，但是可能影响了很多其他的学问上。
应用数学是要从应用以及技术角度看，以应用场景为导向的数学研究。
我们是从事应用研究，就是要解决实际问题，
而这个实际问题一定来自于社会经济发展的重大需求。
陈市长大概3年前，邀请我到他的办公厅里边交流。他期望我办一个以基础数学来发展应用数学的一个研究院，期望这个研究院能够带动中国的基础科学的发展。
我们有75%的应用数学，25%的基础数学，其中想的是把基础数学和应用数学真正的结合起来，然后起到一些引领的作用。
所以我们一开始就重视了怎么引进人才。
我是2019年从新加坡国立大学回国的嘛，大数据的人工智能应用的，其实在欧美已经有非常红火的，但是中国的情况呢，几乎是学科空白。我也大量的组织了很多活动，跟同行怎么来把这个 空白的领域呢给它建设起来。
我一直认为教学是第一重要的，因为我们要培养人才。我们选的学生呢，都知道要充分能够享受雁栖湖的资源，他们也对雁栖湖非常的渴望，非常期待。
因为我们的年轻人这个水平很高，也因此能够吸引到世界上有名的大师。
When I was younger, math brought me joy because I was just naturally good at it. But when you study enough math, you learn that math is really hard. And so maybe some of the joy disappears and is replaced by curiosity and is replaced by a sense of challenge and accomplishment.
具体到我们这个比姆萨这个地方，有我们也自己的特色，我们能够跟来自世界很多国家的学者，来自不同的学科领域的学者，能够做到一些跨学科的深度的交流。
所以我们决定了明年办一次国际基础科学大会。
这个大会是很难得的一个机会，因为这是一个顶级的盛会，然后参会的嘉宾级别也很高，这种诺奖、菲尔兹奖、图灵奖三大奖，包括国际大奖的这个嘉宾数十位。
I think that during this conference, that many distinguished scientists will come here. They will invite us and say, we want also to come to BIMSA. I hope all the people who come to ICBS have a good experience and appreciate the effort that's gone into organizing this conference.
我们现在跟国科大、跟百行有联合培养的学生，这些学生呢来自不同的领域，有纯数学与应用的，甚至有经济管理方面的一些学生加入我们这个大家庭。
There is a joint program between BIMSA and the University of Chinese Academy of Sciences to accept PhD students. I will start to supervise few students from there.
I think the biggest obstacle for women in science in general are people who want to protect them or protect us. I don't need to be protected. That's the worst part, because that's limit my abilities to go further.
经常连做梦呢，然后都是在考虑这些问题。有时候做梦呢，然后就感觉好像是找到了思路，然后半夜就爬起来，然后去验证。就是如果你做梦的时候还没有梦见你在做的东西的话，那估计论文呢还是暂时写不出来的。
我所遇到的这个挑战呢，就是说，我需要找到一条属于我自己的这个路线去做科研。
直到2023年5月，研究院期间累计的引进了科研人员150名，并且初步的组建了量子信息跟量子计算、区块链跟密码学、计算数学、数字经济、统计学、数学物理、代数突破跟应用、生物信息、分析、控制论、数论、代数几何、广义相对论、弦理论、量子场论跟核子系统、微分几何，一共17个不同的方向的科研团队。
我们热诚欢迎世界各地热爱数学的科学家加入北京雁栖湖应用数学研究院，
与我们进行深入的学术交流，让我们一同去探讨科学最美妙的地方，
为我们中国、为世界的数学事业贡献我们的力量。
数学是很有意义的一个学问，我们解决一个好像表面上一个简单的问题，但是可能影响到很多其他的学问上。
应用数学是要从应用以及技术角度看，以应用场景为导向的数学研究。
我们是从事应用研究，就是要解决实际问题，
而这个实际问题一定来自于社会经济发展的重大需求。
陈市长大概3年前，邀请我到他的办公厅里边交流，他期望我办一个以基础数学来发展应用数学的一个研究院，期望这个研究院能够带动中国的基础科学的发展。
我们有75%的应用数学，25%的基础数学，其中想的是把基础数学和应用数学真正的结合起来，然后起到一些引领的作用。
所以我们一开始就重视了怎么引进人才。
我是2019年从新加坡国立大学回国的嘛，大数据的人工智能应用的，其实在欧美已经有非常红火的，但是中国的情况呢，几乎是学科空白。我也大量的组织了很多活动，跟同行怎么来把这个空白的领域呢给它建设起来。
我一直认为教学是第一重要的，因为我们要培养人才。我们选的学生呢，都知道要充分能够享受雁栖湖的资源，他们也对雁栖湖非常的渴望，非常期待。
因为我们的年轻人这个水平很高，也因此能够吸引到世界上有名的大师。
When I was younger, math brought me joy because I was just naturally good at it. But when you study enough math, you learn that math is really hard. And so maybe some of the joy disappears and is replaced by curiosity and is replaced by a sense of challenge and accomplishment.
具体到我们这个 BIMSA 这个地方，有我们也自己的特色，我们能够跟来自世界很多国家的学者，来自不同的学科领域的学者，能够做到一些跨学科的深度的交流。
所以我们决定了明年办一次国际基础科学大会。
这个大会是很难得的一个机会，因为这是一个顶级的盛会，然后参会的嘉宾级别也很高，这种诺奖、菲尔兹奖、图灵奖3大奖，包括国际大奖的这个嘉宾数十位。
I think that during this conference, that many distinguished scientists will come here. They will invite us and say, we want also to come to BIMSA. I hope all the people who come to ICBS have a good experience and appreciate the effort that's gone into organizing this conference.
我们现在跟国科大、跟百行有联合培养的学生，这些学生呢来自不同的领域，有纯数学与应用的，甚至有经济管理方面的一些学生，加入我们这个大家庭。
There is a joint program between BIMSA and the University of.
I'm going to start the talk of this afternoon. So the first talk is given by Xu Kai from Harvard University. The title is Modular of Vector Bundles on Curve and Semi-Orthogonal Decomposition. Let's welcome.
Thank you. Thank you. It's my great honor to be here. So I will talk about my work on semi-orthogonal decomposition of the moduli of vector bundles on curves. We will work with fixed field K of character. We will work with fixed field K of characteristic 0, and it's not necessarily algebraically closed. For example, we can work with Q, and we fix a smooth trajectory curve over this field. Then we can define two closely related moduli spaces. The first is the moduli stack of all vector bundles with a fixed rank and determinant over this curve. And the second is the coarse moduli space of all semi-stable vector bundles with fixed rank and determinant over this curve. So these two moduli spaces are closely related, but they are quite different mathematical objects. The four moduli stack is a smooth and formally proper Artin stack of infinite type, and the coarse moduli space is a Fano variety with Gorenstein canonical singularities. So the blue words are what makes them simple, and the red words are what makes them complicated. We will study the bounded derived category of these two objects, and we will denote it by this dB. we know that for smooth projective variety, the bounded derived category or coherent sheaves is a very well-behaved mathematical object. It's a smooth and proper category, and it encodes the brain structure in the topological B model with this target. However, for singular variety, the bounded derived category is not well-behaved. A mathematical reason is that the coherent sheaf may not admit a resolution by vector bundles for singular varieties. And the physical way to say it is that as the singularities, we have fractional branes, which is not encoded in the bounded derived category or coherent sheaves. So we must add something new to describe the physics. And the correct mathematical notion to encode the brane structure with this target is the so-called minimal categorical resolution of singularity of the bounded derived category, which we will denote it by this tilde. So in mathematics, we know that there must exist a categorical resolution of singularity, but we don't know if there is a canonical minimal one. But from physics, we expect that we should have a canonical minimal categorical resolution of singularity, which encodes the brane structure. One may ask, why do we want to study this bounded derived category of this moduli space? There are two different reasons. So it's related to supersymmetric gauge theory in physics. Bershasky, Johansen, Sado, Van Waffa, they introduced topological reduction of four-dimensional supersymmetric gauge theory to 2D by compactifying on a Riemann surface. And Kapustin-Witten showed that in the maximal supersymmetric case, the S-duality applied to this compactification has a very profound categorical consequence, that is the geometric long-length conjecture. And our work is an analog for this Kapustin-Witten story for less supersymmetric case. We can see that in the n equal to 2 case, this reduction also has something to do with categorical structures of the bounded derived category. And another reason one may want to study this is that the semi-orthogonal decomposition of final varieties, they encode very deep and motivic information in algebraic geometry. The motivic decomposition of this moduli space was previously studied intensely. We have very nice motivic decomposition, which generates a lot of conjectural semi-orthogonal decomposition. And we can see that by other method, we can prove a lot of these previous conjectures. Okay, so let me state my main theorems. The first main theorem is a semi-orthogonal decomposition for the full moduli stack. We can decompose it into a number of pieces labeled by an integer and r-1 non-negative integers. This integer labels the power of the determinant line bundle over this moduli stack. And these non-negative integers give rise to a product of symmetric powers of x. And actually, they correspond to a dominant weight of the related Lie algebra, SLR. Okay, so here, this bounded derived category of the full moduli stack is the brane from other branes from the 4D gauge theory compactified to 2D. When we compactify a gauge theory to 2D, sometimes we have residual gauge symmetry. And this category actually remembers this residual gauge symmetry in 2D. And our second main theorem gives a decomposition of the coarse moduli space. It looks very similar. It's labeled by an integer k, which corresponds to a power of the theta line bundle. And a number of non-negative integers corresponding to a dominant weight. So here, we don't have the determinant line bundle because determinant line bundle only lives on the full moduli stack. It does not descend to the coarse moduli space. A power of it, called theta line bundle, descends to the coarse moduli space. So, so here, we only have this theta. We don't have that L. And here, because our coarse moduli space is a finite type thing, we, of course, when we decompose it, we will decompose it into finitely many pieces. So this data lie in a finite set, which I will define in the next page. And what is this bounded derived category? This bounded derived category describes the branes from the two-dimensional sigma model. When we compactify a 4D gauge theory to 2D, we may approximate this theory by a two-dimensional sigma model. That is, we forget about the residual gauge symmetry and only remember the target. And then this category describes this sigma model. And this decomposition is in particular compatible with the motivic decomposition and also the BGSV computation of the quantum cohomology of this coarse moduli space. Okay. So how do we define the finite set? The finite set S is defined by a very explicit, although a little bit complicated, set of inequalities. So basically, in the Harder-Simhan filtration, each stratum would give us two these inequalities, and we have a lot of very explicit but complicated inequalities. But in examples, we can work it out in a more clear way. For example, the first example is the moduli of rank 2 bundle, and for simplicity, we ask the degree of L to be odd, so that this coarse moduli space is a smooth manifold. There is no singularity here. And then this decomposition tells us that this this derived category of the moduli space decompose into 2 copies of points, 2 copy of X, 2 copy of symmetric sim 2X, until 2 copy of sim G minus 2X, and 1 copy of sim G minus 1X. So conjecturally, these are everything, but I don't know how to prove it. So I should see that there is this ... which is the orthogonal complement of the previous stuff. But conjecturally, this ... is 0. So this statement is conjectured independently by Narasimhan and by Bellman, Galkin, Mukhopadhyay. So this is the first non-trivial example. And the second non-trivial example is the rank 3 case. And we see that we may decompose it into 2 copy of points, etc. And for 2 copy of this sim K1 cross sim K2X, if K1 and K2 are less or equal to G minus 1. But when both equality hold, there is only 1 copy. So yeah, this is previously conjectured by Gomez-Lee based on the motivic decomposition of this moduli space. So these are my main theorems. Any questions up to this point? General reductive group. Yes. We should certainly expect there are such results. And after I explain my proof, you will certainly believe that at least for classical group, by similar method, we can prove such results. Although I haven't worked it out, but for exceptional group, my proof does not work. But certainly, I still believe there are such decompositions. Samuel, they are this order from smaller k to from smaller lambda to larger lambda, but you can also reverse the order by mutation. K lambda. Actually, you can show that there is no map. Okay. So we have this D L tensor K tensor L tensor K tensor D sim lambda 1 X cross. So there is no map from center L tensor D sim mu x. There is no map except when L minus K is non-negative, and this mu minus lambda is dominant. And in root lattice. So actually, there are very few maps. It's more than a semi-orthogonal decomposition into a line. It's something like a square. Yeah, sure. What does what mean? Oh, yeah. Okay, yeah. I should certainly explain this. Thank you for asking. So basically, if we have a category C, we see that C is equal to C1, C2. If C1 and C2 are this full triangulated subcategory of C, and there is no map. If no map, there are no map from C2 to C1, and this CI as full triangulated subcategories which generate C together. So you may have heard about something called full exceptional collection. So basically, we can decompose a category into a number of objects if they are full exceptional collection. This semi-orthogonal decomposition is a generalization of full exceptional collection. Basically, in a full exceptional collection, the objects are labeled by a finite set. In this semi-orthogonal decomposition, the objects are not labeled by a finite set. They are labeled by a finite collection of varieties. Yeah, thank you for asking me. How morphisms are defined. I will explain how categories are defined, but the data of the morphism is encoded in the data of this big category. Yeah, I will also, of course, explain how the functors are defined, how we embed the right-hand side into the left-hand side. I will explain this. Okay, so any more questions before I proceed to the proof of the theorems? Yeah. No, I cannot show this ... is 0. But to prove this theorem, I will need a local analog of this theorem, and in the local case, I can show the ... is 0. Phantom category. Okay, so phantom category means that the Hauschild homology is 0. Yeah, so basically, when we compute something like quantum cohomology, it does not contribute. So yeah, because to show a category is 0 is very difficult, but to show some cohomology is 0 is much easier. Okay. Okay, let's proceed to the proof of the main theorems. The starting point of the proof is the so-called Wei uniformization. So let's first consider the case when the bundle is trivial. That is, we consider the moduli stack of rank R bundle with trivial determinant. This is equivalent to the moduli of SLR principal bundle over this curve, because SLR principal bundle is nothing but a vector bundle with trivial determinant. And it's classical. It's well known that this moduli stack of principal bundle can be written as a double coset given by this loop group, this current group, and this group of rational function. This basically follows from the very simple fact that a principal bundle is glued by trivial bundles, and the locally the transition function are given by mapping from the punctured disk into this structure group that is SLR. So this is a very classical fact called Wei uniformization. But for our purpose, we do not only want to understand this moduli or bundle with trivial determinants. We want to fix possibly non-trivial determinants. And we can show that this moduli can be defined as some moduli of twisted SLR bundle over this curve. And we can also prove a twisted version of the Wei uniformization, which is only slightly different from the original classical Wei uniformization. They differ by an outer automorphism of this embedding given by this line bundle L. Actually, we only need the degree of this line bundle modulo R. So using this Wei uniformization of the moduli stack of bundles, we can reduce the computing of cohomology on this moduli stack into these group theoretical problems, into problems about these three groups: this loop group, this current group, and this group of rational function. Loop group basically is the holomorphic map from punctured disk to SLR. This current group is the mapping from non-punctured disk to the this group SLR, and this is the group of rational maps from the Riemann surface to SLR. Yeah, so this representation as a double coset allows us to reduce the study of tautological bundle and derived category to representation theoretical problems about loop group, current group, and this group of rational functions. But this group of rational functions is the simplest. It plays no role here because of its homological contractibility, proved by Gisgri and Rosenblum. Basically, this means that when we compute cohomology, we can just ignore this group of rational functions. They play no role here. And the representation of this loop group is very clearly understood in a geometric way by the Affan-Borel-Weibo theory. Actually, we need a little more from the usual Affan-Borel-Weibo theory. The usual Affan-Borel-Weibo theory deal with one piece of this loop group. But here, we are dealing with infinite product of this loop group labeled by points on this Riemann surface. So we need a factorization version of this Affan-Borel-Weibo theory, which is formulated in the language of chiral algebra, and in this case, the so-called West-Zumino-Witten chiral algebra. But this is already well understood before my work, basically by Beilinson, Drinfeld, Gisgri, Rosenblum, etc. And our main theorem is finally reduced to a fact about this current group. And it's reduced to the following fact, that we have a semi-orthogonal decomposition for the representation category of this current group into a number of subcategories like this. So basically, this subcategory are products of symmetric powers of the disk. So they are labeled by lambda 1 to lambda r minus 1, which is dominant weight of this Lie group SLR. And our main theorem is reduced to this theorem. So actually, with a little bit more effort, we can show that this dot 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 actually vanishes, although we don't need it in the proof of our main theorem. So now we can observe a very nice fact that our main theorem care about this derived category of the moduli or bundles over a compact Riemann surface. But we may also ask, what happens if this X is not compact? What happens if X is a disk? In this case, there is our bundle has a lot of automorphisms. The automorphisms are given by mapping from the disk to the SLR, to the structure group. This is nothing but the current group. So this derived category of this moduli or bundle is nothing but the representation of the current group, which is exactly the left-hand side of this theorem. And we directly see that this theorem is actually a local version of our main theorem. The only difference between this theorem and the main theorem is that in the main theorem, we also have a determinant line bundle here, but only in the compact over a compact Riemann surface, we have this determinant line bundle. In the local case, we cannot define the determinant line bundle. So yeah, this explains the difference between the local version and the global version. Okay, so now we see that to prove the the decomposition of the moduli stack, we only need to prove this local version, which is a representation theoretical statement. And before we proceed, let's think how we can construct the functors. We haven't defined. We haven't say how do we construct the functors from the right-hand side to the left-hand side. So a natural choice of these functors is given by the tautological vector bundles. They can serve as Fourier-Mukai kernels to define this Fourier-Mukai transform. But where does the tautological vector bundles live? They naturally live on this xn cross the moduli stack. And by this Sn equivariance, they naturally descend to the static quotient of x times this moduli stack. But we see that it is not directly related to the classical symmetric power. This is the static symmetric power, and we want the classical symmetric power. And actually even more, we want products of classical symmetric power. We don't see here how they are related. A key observation is that these products of classical symmetric power, they appear as a static stratum of the static symmetric power. So here we only consider one static symmetric power, not a product, but the products of classical symmetric power appear as static stratum in the single copy of static symmetric power. And we may naturally guess that this static stratification actually gave us a semi-orthogonal decomposition of this bounded derived category into the derived category of these guys. And this is actually a theorem of Polishchuk and Vanderburg. And although this seems very natural, very innocent, the proof is very, very deep. It's essentially based on Lustig's construction of Hecke algebra by Springer correspondence. And they use essentially some formality results about the l-adic sheaf. So I don't know a proof, for example, over C. But anyway, we know that there is such a decomposition. So we see that the right-hand side of this decomposition we want also appear in the derived category of static symmetric power of the disk. And this decomposition would give us a relation between the representation of current group and the static symmetric power of the disk. So let's see how we can come up with such a relation. This is maybe a little bit not so well known, but we may also consider another local example given by the GM, that is C star. GM is another name for the C star, or A1 minus a point. Then, if we take x equal to C star, by similar reasoning with this, we see that the moduli of bundle is the classifying stack of the alpha and Lie group. And so its derived category is the representation category of this alpha and Lie group. And similarly, the right hand, what is this guy, this symmetric power? This static symmetric power the derived category of this static symmetric power can be written as the representation category of this Sn semi-direct product with Dn. This basically follows from the simple fact that the derived category of Gm or C star, they are the same thing. This is equal to the representation category of Z. And this implies that the derived category of its static symmetric power is the representation category of Sn semi-direct product with Zn. And what is this guy? This guy have a name called alpha and Weil group of type A. And this relation we want is actually some relation between alpha and Lie group and alpha and Weil group, which reminds us of the well-known alpha and Schur-Weil duality, which connect these two guys. And by replacing this Gm with the disk, we get a close cousin of the alpha and Schur-Weil duality, which is named Schur-Weil duality for current groups. It's not as well known as the alpha and Schur-Weil duality, but the proofs are basically parallel. So now it seems we are done, but not actually. So unfortunately, both alpha and Schur-Weil duality and Schur-Weil duality for current group were only proved on the abelian level in the literature, and the derived version does not directly follow from the abelian version. So in the classical Schur-Weil duality, the derived version follow from the classical version because the abelian category is semi-simple. But for the alpha and Lie group and current group, their representation category is not semi-simple. And an embedding of the abelian category not necessarily induce an embedding of the derived category. However, based on the highest weight structure on both representation category, we can give a proof of the derived Schur-Weil duality for current group, which actually implies the decomposition of current group we want. So what does this derived Schur-Weil duality say? This basically says that the Fourier-Mukai transform associated with the tautological bundle on this product give us a functor from the static symmetric power of the disk to the representation of the current group. And as we know from the classical Schur-Weil duality, in general, this functor is neither fully faithful nor essentially surjective, because the representation of symmetric group is very different from the representation of the special linear group. However, if we restrict it to the subcategory we want, the derived Schur-Weil duality tells us that this gives us a fully faithful embedding from this derived category of products of symmetric power into the representation category of the current group. And if we take this n larger and larger, these subcategories actually exhaust the representation category of the current group. So this is the derived version of Schur-Weil duality for current group, and this theorem directly proves the decomposition of the representation category of current group we want. Okay, so now we finish the proof of our first main theorem. So any question up to this point? D equal, yeah. It's a slightly different version of the current group. Yes. D. Yes. I will certainly agree with this. Yeah. Yeah, but the problem is that the symmetric power of A1 is easy, but this current group version of A1 is slightly more complicated. Yeah, so yeah, but I would certainly guess that this theorem I still holds if you replace the disk by the by A1 and what else? Yeah. Yeah, and it might happen that the current group for A1 has a lot of infinitesimal direction which is not integrable. It might happen. I'm not sure. Okay. So any more questions? Yeah, please. Yeah. Actually, I'm not very very familiar with these concrete examples in. Yes. Okay. So basically, we can pick a point on the right hand side. I can tell you what this corresponds to in the left hand side. Basically, the simplest thing on the right hand side corresponds to the so-called global while module on the left hand side, which is explicitly defined representation of the current group by generators and the relations. It's basically when we consider the representation of a simple Lie algebra, we have while module. We can write it by generator relation, and in this case, we can also define this while module. They corresponds to the skyscraper shape for quant on the right hand side. But there are much more complicated representations other than while modules, and if you can decompose a representation into these global while modules, you know what it corresponds to on the right hand side. Basically, I can tell you the generators on both sides and match them, but they are more complicated things than generators. No more questions? Okay. So, what kind of isomorphism? Oh, sorry. Could you say again? I didn't get it. Yes. Yes. In terms of isomorphism as stack. A priori, it looks like it's infinite dimensional, but it turns out it's finite dimensional. Okay. So now let's proceed to the proof of the second main theorem, that is the decomposition of the coarse moduli space. So we may ask, after we figure out what happened for the full moduli stack, how do we study the coarse moduli space? Of course, we want to relate these two guys. They are related by a sequence of maps. So first, we may consider a moduli stack which consists of only the semi-stable vector bundles. So this semi-stable, the moduli stack of semi-stable vector bundles is an open substack of the 4 moduli stack. So on this open substack, is a finite type thing, is a finite type stack, and a generic point in this moduli stack, that is the generic semi-stable vector bundle, would have the automorphism group given by mu r. Mu r is basically the rth root of unity. Given a generic vector bundle, its automorphism group is just the scaling. And if we want to say that, if we want to require that this automorphism acts trivially on the determinant, we see that we must scale by a rth root of unity. So a generic point here would have isotropic group given by mu r, and we may rigidify this generic isotropic group. That is, we may quotient this by b mu r, that is the classifying stack of mu r. This is a rigidification map to another stack. This is still a stack, but this has much less isotropic group. A generic point here does not have any non-trivial isotropic group, but at some special points, they are non-trivial isotropic group. And this rigidified moduli stack admits a map into this coarse moduli space. So we see that we have related this 4 moduli stack and the coarse moduli space by a sequence of maps. And let's look at these 3 maps one by one. So this map is, although this map behaves very complicatedly on geometry, at a categorical level, this is exactly what we want, because we have said that this guy is in general singular. The derived category of a singular space, it does not behave well, and we want to take its categorical resolution of singularity. And this map on the level of derived category is exactly a categorical resolution of singularity. So this is exactly what we want. And then we also know that if the degree of L is co-prime with the rank n, then this guy is actually non-singular. And in this case, we don't want to do anything. And actually, we can also directly see that if this guy is already non-singular, this map is just an isomorphism. This indeed doesn't do anything. Okay, now let's look at the second map. The second map is just a quotient by b mu r. This b mu r is a group stack, and such a quotient map behaves very simply at the level of bounded derived category. This quotient map basically says that the derived category of this guy is the invariant part of the derived category of this guy under the b mu r action. And this invariant part construction is very easy to take. And at the categorical level, this is easy to study. And then when we look at the final map, although this map is an open immersion in the geometry, at a categorical level, it's terribly complicated. So the only thing we need to study is how the derived category behave when we restrict from the 4 moduli stack to the semi-stable open substack. And our reduction from the 4 moduli stack to the semi-stable open substack is highly motivated by some machinery called derived theta stratification, developed by Harper-Lessner, which allow us to relate the derived category of the 4 moduli stack and this open substack. So what's the basic idea? The basic idea is to apply the excision sequence to compare the homomorphism in the 4 moduli stack with the homomorphism on the semi-stable open stack. And the excision sequence says that we have such an exact triangle. In the middle, we have the homomorphism on the fourth thing. Here, in the right, we have the homomorphism on the open substack, and their difference is given by a compilely supported cohomology, that is, those supported on the unstable locus. And we see that in very good situations, if this guy is 0, then we know that the homomorphism on the semi-stable locus is equal to the homomorphism on the 4 moduli stack. Of course, this does not always happen. Actually, it happens in in very rare situation. When does this happen? Basically, we use the following fact that if we take the global section on BGM and a coherent sheaf on BGM is just a representation of GM. This is 0 if M is has non-zero weight. And by this observation, we see that in some situations, when we pick a particular objects E and F in this derived category, that is E and F are vector bundles living on this 4 moduli stack. If the weight of E and F satisfy some constraints, we know that this cohomology supported on the unstable locus is 0, and then we see that their homomorphism on the 4 moduli stack is equal to the homomorphism on the semi-stable locus, and in this way we can get the semi-orthogonal decomposition we want on the semi-stable locus. And actually, this explains what this explains in our second main theorem. How does this finite set S come from? This finite set S is defined by a number by a collection of inequalities. Each inequality comes from a stratum in the Harder-Narasimhan stratification. That is, each unstable vector bundle would give us such an inequality, and this inequality basically says that the corresponding cohomology group supported on that strata is given by 0. There are infinitely many. Infinitely many inequalities, and they cut this collection of integers and positive integers into a finite set, which gave us the decomposition of the derived category of semi-stable locus. Okay, so this is the proof for our second main theorem. I think I should stop now, and thank you very much for attention. Please. Yeah, but he talked about l-adic sheaf, and I talk about coherent sheaf. Yeah, very, very different. So yeah. I don't know. I don't think so, because I use these tautological bundles. They are. Yeah, I think these two stories are completely different, and actually, his story is related to the maximal supersymmetric gauge theory, and my story has less supersymmetry in physics first. Thank you.
There's no break, right? So the next talk. 已经考上去了。好，那直接你试一下是不是直接开始？直接开始是吧？Okay. The second talk of this afternoon is given by Hongjie Yu from Weizmann Institute of Science. The title is Counting l-adic Local Systems Over a Curve. Let's welcome.
So I will talk about counting l-adic local system over a curve, and let's start with some background, basic thing. So in fact, the main subject is about a function field. A function field is by definition a finite extension of FPT, and we know that there is a unique curve such that f can be realized as the field of rational functions over f. So in fact, f is a finite extension of fpt, and we can indeed to choose it to be separate. And we know the curve is just, we consider the O1 as the integral closure over fpt, and then we have a spectrum O1, and we can also consider another integral closure as the fp 1 over t, and then we have a spectrum O2, and then we glue these two spectrum and get a curve. And one principle is that what applies to a number field applies to f as well. And since we are considering curve, we have another principle says that what applies to a Riemann surface applies to the curve. So there are several examples to apply this principle to use a geometric method to solve arithmetic problems. For example, the Riemann hypothesis, which is far from be able to be solved in number field case, but over function field case, it is a theorem of Deligne in 1974, and the long-length correspondence and the Ramanujan conjecture over number field case are also not solved for now, but over function field case, they are solved by Laurent Laforgue. Yeah. To apply such a principle to the question we will be interested in, we need to introduce the fundamental group. So for a Riemann surface, we know that the fundamental group of a Riemann surface is just defined as the homotopy classes of loops over the Riemann surface. But this is not a very it's not an algebraic definition, so we cannot adapt it to positive characteristic to an abstract scheme. Another one is to use a property of the fundamental group using the DAC transformation. We know that given Riemann surface and considering a universal covering, then the topological fundamental group can be defined as the automorphism group of this universal covering. And using this, if we specify what are coverings, then we can define the fundamental group. So we have the theory of étale site, and then we can define étale coverings. And using étale coverings, we can define the topological, the étale fundamental group. So it's just since in algebraic category we do not have a universal covering, because we can already see in the case of Riemann surface that a covering is usually defined by exponential map, which is not algebraic. So we need to restrict to finite coverings. And then so the pi1 étale of x with a base point x is defined as the projective limit of automorphism group of finite étale coverings with yy finite étale coverings of xx. Then this is a finite group, and it is defined as the projective limit, so it carries a topology. And so pi1 étale is a profinite group. The étale fundamental group can usually reveal hidden structures of varieties which we cannot observe purely by its point. For example, we know that the spectrum of FQ is a point, but its étale fundamental group is isomorphic to the Galois group of FQ, and which is isomorphic to the Z-hat. So, which is generated by one element. So it's a profinite completion of Z. So the spectrum of FQ looks more like a circle instead of a point. And we can specify a generator, and the generator is given by a Frobenius element, which sends element X to its Q power. So the group generated by Frobenius is dense in the étale fundamental group, and pi1 étale is topologically generated by one element. And we have a short exact sequence that in the middle term we have étale fundamental group, and it admits a normal subgroup, which is the so-called geometric étale fundamental group, which is the étale fundamental group of the base change of X to FQ bar. And the quotient is isomorphic to the Galois group of FQ. So if we have a Frobenius here, then we can lift it here and X by conjugation here. The action depends on a choice, but it only depends the choice up to an inner automorphism. So let me give you some example to see that the étale fundamental group is not really abstract. So the pi1 of P1 is trivial. So this is analog of the number field case that there is no everywhere unramified extension of Q. Another less trivial example is an elliptic curve. So we know that for elliptic curve, there are two cases. Either E is supersingular, then the étale fundamental group is isomorphic to the product of ZL square for L different from P, or E is ordinary, then pi1 étale is similar as the same thing, but we need to productive is ZP. So it is generated by two elements because we can write it in this way. It's, as we know in the topological case, the topological fundamental group of an elliptic curve is Z square. And in our algebraic case, it is either Z times ZP, or is Z hat quotient ZP square. Okay. So it is similar to the topological case that it is generated by two elements. topologically. And however, if things becomes more complicated, then there are no explicit presentation for Pai-Wan et al., which the Frobenius action will be more mysterious. So to understand the Pai-Wan et al., we can understand it through its representations. So given we're interested in linear representations of Pai-Wan et al., so it means the isomorphism classes of homomorphisms from Pai-Wan et al. To JNK. So K here is usually a topological field. So, and to take the topology into account, we need to consider continuous representations. But we need to carefully choose a field. We know usually we consider the field of complex numbers, but the topology of C is very different from profinite topology. Another choice is QL bar. As an abstract field, it is isomorphic to C, but they have very different topology. So then we can try to use a QL bar coefficient, and however, we need to exclude one case that L is equal to P, because when L equals to P, then the QP coefficient does not work very well with the et al. Topology. So we choose, we're now considering L different from P, but L can vary. So we consider the set of representations of irreducible representations of Pai-Wan et al., and then the geometric Pai-Wan et al., and then in it we have a Frobenius action, which is given. So as I have mentioned, the Frobenius action depends on the lifting of Frobenius, but the dependence is only up to an inner automorphism. So if we consider the set of representations, then we cannot see this inner automorphism. So we have a well-defined independent of choice action of the Frobenius on the set of elements of Pai-Wan et al. And however, one remark is that the set MNL depends on L. We can already see this when n equals to 1. For example, there is an easy exercise that you can check the continuous homomorphism from Z hat to Q bar inverse is isomorphic to ZL cross. So which is indeed depends on L. But one surprising fact is that if we look at the Frobenius action together with this set, then we will get some different phenomenon. So let's look at the case of n equal to 1. Then we know by class field theory that if we consider a one-dimensional representation, which means a character of Pai-Wan, of geometric Pai-Wan et al., then suppose sigma is fixed by the Frobenius action. Then the image is finite. So it means that the image is contained in GL1 Q bar, which is independent of L. And we also know by class field theory that the number of fixed point is finite, and this finite number can be expressed as the FQK points of a variety, as already mentioned in yesterday's talk. The right-hand side of this equality is the number of FQK points of a variety over FQ. So we can use a Grothendieck-Lefschetz trace formula to have a more precise expression. We know that the FQK points can be calculated as the alternating trace of Frobenius acting on cohomology with compact support. So as we know how to calculate the cohomology of the Picard variety of the curve, then we know that this number is finally of this form. And here the sigma I are Frobenius eigenvalues over H1 of the curve. And by Derlin's proof of Wei conjecture, we know that Frobenius eigenvalues on étale cohomology are special numbers. They're called Q-Wei numbers. These numbers are very good. They are algebraic numbers and algebraic integers, in fact. So, in fact, we see that the number of FQK points of a variety must be some special form. Observing this phenomenon and the phenomenon of article of Drinfeld, later I will mention, Derlin made a conjecture that the above mentioned phenomenon for rank 1 holds for general rank as well. So he says there are Q-Wei numbers alpha and beta, so that family of numbers alpha, in fact I should write alpha I and beta j, which are independent of L, so that the number of Frobenius fixed point is independent of L and can be expressed as the alternating sum of k power of alpha beta. And this is exactly the form that the FQK points of a variety should looks like. And Derlin also gives more predictions about alpha and beta that I will explain later. Here I explain again the Q-Wei numbers, a special type of algebraic number appearing as a Frobenius eigenvalue over étale cohomologies. And so Derlin's conjecture suggests that the number of Frobenius fixed point should behave as if there exists a variety defined over FQ, which is independent of L, such that the number of fixed point looks like the FQK points of the variety. So using Grothendieck-Lefschetz fixed point formula, then we know, because we know the number of FQK points of V, it looks like this form. Here alpha and beta are eigenvalues of Frobenius acting on the cohomology of V. Then we have Derlin's conjecture is based on the n equal to 2 case of Drinfeld, and now it is a theorem for any rank that we prove that there exists a universal polynomial which depends only on G, the rank n, and such that for any FQ, here indeed it is for any characteristic P and any FQ of characteristic P, and for any curve over FQ of genus G and any L different from P, the number of Frobenius fixed, the k iterated Frobenius fixed point can be expressed by evaluating this polynomial in Q-Wei numbers of Frobenius acting on H1 of the curve. Moreover, we know explicitly the degree and of the polynomial and the evaluating to 1 of this polynomial. We have some more information about this polynomial is that it is divisible by PG1. And these properties about degree, the evaluating of this polynomial to 1, and the second property is indeed the second part of Derlin's prediction. He conjectured that we should have such a form. And have I explained it? Okay, yeah. So So why the Lin conjecture this, and what does it mean of the degree and evaluating of this polynomial to 1 is that if, for example, if we have a V, the FQK points of a variety V defined over FQ, so that the V, the number of FQK points of V can be expressed by some polynomial or simply by some by Q-way numbers. Then from these Q-way numbers and the Grothendieck-Lefschetz fixed point formula, we can see some topology of V. So indeed, we know that dominant term determines dimension. And if we, so here is I and J, if we evaluate I to 1, evaluate I to 1 and J to 1, then this equals Euler characteristic of V. So, yeah. So the Lin's conjecture, in fact, says if there is such a variety, he has a precise prediction on the dimension and the Euler characteristic of this variety. We can, so a natural question is it possible to give a algebraic structure and understand it in a more conceptual way? So the first thing, we know that the first difficulty is that, as I have explained, the set depends on L, and it seems very difficult to give M and L a structure of variety over FQ bar. However, there is a way to give it a structure of stack, but not over FQ bar, it's over QL bar. So in an article of Aronkin, Gascory, Kashtan, Raskin, Rosenblin, and Warshawski, that there is an algebraic stack of all local systems of rank n over the algebraic closure over X over algebraic closed field. So here it is not about irreducible local system, it's about all local systems. And these algebraic stacks lives over QL bar. It's classifying all rank n continuous l-adic representations of pi 1 et al. And we have a Frobenius action on these algebraic stacks. It looks very interesting and indeed has many applications already, but this does not explain the Lin's conjecture because the geometry of this local system is far from what we have observed from the counting phenomenon. For example, an irreducible local system which lives in this space lives in an irreducible component. So I mean, so it gives an irreducible component. So it is in some sense very discrete. And but so first of all, it cannot explain the dimension Euler characteristic phenomenon. Lin also suggests to approach the problem from p-adic side, and we have seen yesterday a talk constructing a algebraic stack in p-adic side. This may be closer, but still it has a long way to achieve the goal. So one question is, can we find a variety V so that the number of FQK points can be expressed in this form? In the previous theorem, we give a polynomial, but now we want to construct a variety V. Of course, the variety V usually, even if it exists, it will not be unique. And so, because we only know its FQK point is not enough to know V itself. But if we can construct some nature V, we may hope to approach to find out how to understand the Lin's conjecture conceptually. And the answer is yes, we can do this in some ramified cases. So the ramified version is very similar as the previous version. We just consider an affine curve. So it is a curve x minus a finite set of points. Then we consider the set of l-adic local system over x minus s. By local system, I mean irreducible continuous representations of the étale fundamental group of x minus s. And then we have a Frobenius action if Frobenius, because the set S is defined over FQ. However, unlike the previous result, the fixed point is infinite. So we have indeed we have an infinite partition of the set following the ramification around each puncture. So the set of l-adic local system over x minus s can be expressed as a disjoint union over some subset, and the index R is the ramification type around each puncture. Then, by long-length correspondence and the theorem of Harder, we know that the number of fixed points is finite. So if the ramification is trivial, then we get the unramified case, and which is the previous treated case. Deligne also hoped that if R is timely ramified, we can expect a similar conjecture. Indeed, he expects that whether or not R is timely ramified, the similar conjecture of should be correct. But so I mean, the number should be expressed by Curie numbers. But only in the timely ramified case, he give a prediction on the dimension and Euler characteristic. Okay, so and Deligne also specify a special case, which he says in most cases we call it generic case. That in most cases a better result is expected. But in fact, he says in this case the proof should be easier. So we go to this. We will explain what this special case is. So I will skip the ramification step. It's just said that the ramification is indeed governed by arithmetics. By arithmetic datum, so by the action of inertial Galois groups. So to motivate the other result in this direction, I will talk about something different. So let's mention some words about Simpson's theory. Simpson's theory is housing more general, but now we are only interested in the case of Riemann surface. So given an integer, a positive integer n, we have two moduli spaces as complex varieties. now I only consider the stable one instead of the semi-stable one. We have M-Betty. It classifies irreducible representations of pi 1 sigma to GLN-C. It has a very explicit presentation of M-Betty. And it can be expressed, it can be constructed using GIT quotient. And we first consider all homomorphisms from pi 1 sigma to GLN-C, and then consider the GLN action and consider the GIT quotient over the stable part, and we get M-Betty. And M-double, we have stable Higgs bundles of rank n and degree 0. So M-Betty is a non-abelian version of H1 Betty, and Higgs bundle is by definition a pair of E and phi. E is a vector bundle, so it's a vector bundle of rank n and degree 0. And phi is a homomorphism from E to E twisted by holomorphic one forms. Simpson theory says we have a real analytic isomorphism between these two spaces, the M-double and the M-Betty. But we know that M-Betty is affine. M-double is almost a projective fibration over affine space. So it is not affine in particular. And so we have indeed two different algebraic varieties, but they are real analytic isomorphism by some explicit homomorphism. And then we consider the TAM case. So yeah, let me add one more word. So M-double, this space exists also over positive characteristic, and it has been constructed and studied by many mathematicians. M-Betty looks like the MNL I have given before, but now we consider C coefficient because here we have a discrete group, so the topology is not important here, and it's much more easier to construct a moduli space. However, over a positive characteristic, we will see similar things. So the general case is the case mentioned by Delin, which are easier to treat. In this case, we have a subvariety M in M-double. Defined over FQ, such that the number of points can be expressed by the number of fixed points of Frobenius acting on MNL with a generic ramification type equals the number of FQK points up to power of Q. In particular, this verifies the Lin's conjecture. So, but next we may ask what about the general case? However, the general case we cannot find one variety, so whose FQK point equals the number of fixed point, but we can find an element in the quadratic group of varieties of FQ, but inverting A1. So the need to invert A1 can be already observed from the identity here. We have the identity holds up to Q's power, okay? Q's power of some negative degree. Moreover, we know how to, this V the theorem is not a theorem of existence, it's explicit, it's constructive, so we know how to represent V. In particular, V involves Emendable and also some varieties, some pika and dimension 0 varieties. The general case looks like this. I have not precise what M is, but I have mentioned the Simpson's correspondence. In Simpson's correspondence, if we imagine we are living in a world of characteristic 0 over Riemann surface, then on the left-hand side, I replace it by M and Betty. Then Simpson's correspondence says this variety over Simpson's correspondence over punctured Riemann surface says this variety is isomorphic to another variety in M and Dobor in the real analytic sense, and this M is the algebraic version of Simpson's variety. So it fits perfectly with Simpson's theory. It's just that we don't know why. So I have 10 minutes. I will mention something about the proof, but only the main ideas of the proof of these theorems. So we're counting, in fact, representations of fundamental group, but by long-length correspondence, it is equivalent to count some Caspita automorphic representations, because pi 1 x minus s is always a quotient of Galois f. F is the function field of the curve, and f is f. So the counting representations of this guy is the same as counting representation of this guy which factor through this quotient. So it means we, by long-length correspondence, we are counting some automorphic Caspita representation of GLN AF. Here A is the ring of Ardels. So the first thing is to precise what this sum means, and then this can be done by local long-length correspondence. And local long-length correspondence is an existence theorem. It says we have a correspondence between representations of a local field and representations of Galois group of the local field. So it is not precise, but it is made precise in the essentially tame case by Bushnell-Enyart. Okay. So then we have we know what automorphic Caspita representation to count, but why we should reduce the problem to automorphic side is that we don't know a space of representations of pi 1 x, but we know that automorphic Caspita automorphic representations lie in a common space. So we have the space of cusp forms, and this is a subspace of GLN AF quotient GLN F. So, and indeed, it lies in the discrete part. It means that so every Caspita automorphic representation. So this is a direct sum of Caspital automorphic representation with pi 2x2 non-isomorphic. So we have this lies in here, but we have other parts. So let me give an example for a GL2 case. In the GL2 case, we know that L2 of this total space is the Caspital part, the completion of Caspital part, direct sum with residue part, and direct sum with continuous part. And here looks like the form of this. This is just a Hilbert direct sum of pi. Yeah. But we know that we only want to count some part of it. The idea is to construct an operator T on L2 such that the trace such that it is compatible with the decomposition. And it has trace T acts, so it acts on each subspace, and the X are pi. And T acting on pi has trace 1 or 0. If pi, we need to count. And otherwise, we give 0. Then the trace of T acting on A cusp equals the number we are going to count, and the ideal way is to calculate the trace of T on L2, and then calculate the trace on L2R and the trace of L2 continuous part, then we are done. And however, the trace of T on this part is infinite, so we have some, we need to use some formula called Arthur-Selberg trace formula that truncate this, the action of T on this part, and basically, here is a rank 2 case. Basically, the calculation of Grunfeld is doing in this way, and then we need the higher rank case is just more complicated, and I stop here. Thank you. Yes, we have. We can consider also the general case. We hope to finally count the l-adic local system for. So for simplicity, let G be a semi-simple split group. And then we want to consider G local system, but because the long-length correspondence is not well understood for the moment, it will be well understood after the recent article of Laforgue and Gascory, when it appears, but now it hasn't. So so we count the G. We count. G Caspital automorphic forms or Caspital automorphic representations, and then so sum, and this sum is the general case as in the GLN case I mentioned. Then in the general case, we know that the number equals a sum of M G. I should write MH FQ. here H I call something I called it co-underscore group. And we have a theorem like this one. Yes. For GLN, the only co-underscore group of GLN is GLN itself. So yeah. And here are Hitchin moduli space that generalize MN double. So yeah.
对，我是下个 speaker， 但我 USB 我不确定要剪，看一下有没有。好，对，我今晚上有一个网友。
Stable no， 你存下，它是不是没保存啊？不关我的事啊，是你存了就拔掉了。
你电脑的。
他没有，他那个头不对，他要转换头。
哎，
没存下来啊。
那没有转换，那昨天的那个。
他没存下来。upload 去哪了？没存下来，我不知道怎么回事。
这蓝牙有办法吗？我一直在这个电那里面吗？可以，我可以用。
在电脑，但是它这个头不是那个 USB， 它弄不出来。刚刚找人，你们工作人员借了一个。
你可以发微信吗？或者发邮箱吗？谁的？可以，谁的？可以。
拿去，不要吵，过去坐着。10分出比较问题。直接一拔没有存。
这网络是因为复旦的网络也可以，或者是你自己的
我昨天有上传那个 PPT 到网页上面，到那个 ICCM 的网页上面。昨天晚上。
你微信给我，我给他好吧？加我微信好吗？可以吗？你微信给我好吧？你这里有微信吗？还是没有网络？
我什么东西给你啊？
你把这个 file 给我。
我这里怎么给你？那个我们没权限的，只能。
你用 Drop， 你用 Apple 的那个 Drop 给我好吗？发给我，这个也可以，连得上的话。加一下。你加一下我，他传给我再给你。
你自己扫码就行了。传到网页上面的，我直接下载就行。
你给我了吗？这个无法登录啊。
我传给你了呀。
我这个无法登录。你要我登这个是吧？
不用。
那你别登，我这个都打开了，等一下别人看不了。我发你行吗？我加你，你把这个关掉，不要用这个，不要用这个。然后我发你，这样比较快。然后我发你，你怎么弄？你去登吗？你确认了吗？加上。
你待会儿用黑卡吗？
我不用啊。
不用。好的。
没事没事，他们应该。我有啊，如果你要，我可以。你有这个的？我有这个的。我有可以转这个的，也可以转这个的。如果你要，我可以转。
哇，那因为他这个更快。
没有，好像对，你这个，然后你就随便放进来就行。
我给你了，还没收到吗？收到。
那它更快，这已经考上面直接。
上回他已经上去了。
哦，也上去也行。
我不能问，不是因为不进。对对对。
可以，会，可以的。
我们那个3:45讲完，是不是后面4点，下一场是4点，对不对？所以你给我多几点时间。
好的，没问题。
好了，你开始。喂。
好。
喂。
OK。
喂。
就你是这个。
哦。OK，great。
Okay, the third talk of this afternoon is given by Huailiang CHANG from Hong Kong University and Science and Technology. His title is Mixed Spin P Fields for Quantic Singularities. Yeah. Let's welcome.
Okay, sorry for the trouble that I'm not sure caused by what, but yeah, I'm going to talk about mixed spin field MSP field for quantic singularity. So it's essentially about Gromov-Witten theory. Because this is a kind of a large subject, I may not be able to start from the beginning. So let me see what can I do in half hour. Okay, so in this talk, the word BCOV will be the part of topological strings in physics paper by Bashasky, Chakotay, Ogri, and Wafa. So these are 4 people who pioneer in the discovery of certain structural result in topological strings. And this belongs to the type 2 string, and it does not belong to algebraic geometry in their paper. And they found a kind of rule called Feynman rule that govern the homogeneous Gromov-Witten theory, which enumerate holomorphic curves in varieties. But that enumeration is in the sense of physics, but instead of arithmetic. So it's actually kind of irrelevant from arithmetic. It's the mathematical treatment in algebraic geometry. Now we find out that it's governed by moduli space of mixed spin P fields. And it was discovered in 2014 and with certain follow-ups. Now, in this talk, I would like to discuss the case for Fermat-Landau-Ginzburg invariance called FGRW invariance. So let me start from the beginning setup. So the quantic Calabi-Yau is a hypersurface defined by this equation in CP4. And there's in physics literature, there's a Landau-Ginzburg partner, which is a, or maybe I should do here. So C5 is you divide it by second group of order 5, and then over it, so this is non-compact, over it you consider this holomorphic function. And then, yeah, so let me introduce Professor Chakotay, the one who just come in. The C for BCOV is here. And W is a holomorphic function on this open complex manifold or OB4, which has critical points to be compact. So this kind of condition is together as a pair is what we call by Landau-Ginzburg pair. It turns out that the smooth projected variety here and this Landau-Ginzburg pair will have very deep relationship, at least for the consideration of physics theories. But I'm sure for arithmetic they surely will be related. And yeah, so sorry. Yeah, so the critical point is a origin. And Landau-Ginzburg mirror symmetry is one of the origin of the current mirror symmetry, if you follow the history. Now, let me go to the part 1 about BCOV conjecture for quantic Calabi-Yau threefold. many string theory contents are not mathematical rigorous yet. Because the path integral is not, the measure is not defined, we are still working very hard to make it definable. And for counting of Riemann surface, which actually belongs to a very specific kind of physics theory, and I mean, many others are not countings, but this kind of counting ones is mathematically possible, made by Gromov and then Witten and then some followers. So let me use this symbol to denote the modular space, or the space of all degree D holomorphic maps from genus G Riemann surface to the quintic Calabi-Yau Q. And this will be compact, and it will be endowed with a virtual fundamental class. This is a cycle in a 0-degree homology class. And it's the easiest way to understand this cycle is that if you deform your compact Calabi-Yau quintic 3/4 complex structure, then this cycle will always be constant. You always look at the holomorphic maps. Holomorphic maps will change, the modular will change, dimension will jump, but inside of which this cycle will be always there. For generic complex structure of Q, if you deform it, the modular space will become this cycle. Now, the Gromov-Witten invariance will be counting the size of this cycle. So this is parameterized by the Riemann surface genus G. You count and of degree D inside the target Calabi-Yau 3/4, and you integrate by 1. Then that means a counting of holomorphic maps. And this NGD is so-called genus G degree D Gromov-Witten invariance of quintic Calabi-Yau. Is extremely difficult to evaluate one by one, and physicists suggest us to put into a series with a generating function, and then regard this as a so-called A model genus G partition function, generating function, I should say. So the history is like this: some path integral in topological string. After B twist some terminology, you get analytic invariant of the mirror Calabi-Yau, and the invariant is parameterized by a genus, and B represent for the B model. And when genus is 0, it's the period of the Calabi-Yau 3/4, and when genus 1 is the analytic torsion involving the Laplacians, all the eigenvalues, theta functions. And for genus larger than 1, it is not mathematically clear which mathematical object it corresponds to. And if you perform another different kind of twist, you will obtain enumerative holomorphic curves invariance in Calabi-Yau. Genus 0, you are counting genus 0 degree D curve. Genus 1, you count genus 1 degree D and larger than 1. These are difficult to enumerate, and putting them in a generating function, you get a partition function in a variable Q. Now, this big Q and small q are related by a coordinate transformation called mirror map. A lot of people have spent time on that. Physicists suggest us that they should be equal after certain identification between the coordinate big Q and small q. The reason that they should be equal because they originate from the same path integral, which actually, I hope in this century, it can be mathematically defined. Now, the periods follows these people's work, Green, Parker, Candelas, and so on. That's a physics work, and genus 0 degree D given by Gimentao and Liang Yao around 1999. Analytic torsion and the higher genus are provided by BCOV, but I mentioned in the beginning in 1993. And for genus 1, even just move from genus 0 to 1, mathematicians need to take 10 years. And the reason is that mathematically, the Picard-Fuchs is relatively easy in a genus 0 story. In genus 0, this is OR class of some finite vector bundle over finite rank vector bundle over finite dimensional moduli, doable. But for higher genus larger than 1 or equal to 1, the BCOV all genus structure, in A side, it is hard to find out its corresponding objects. And instead, the people, Zinger and Zingerli, use stratification of the modular space, try to enumerate it kind of a bit violently to obtain the numbers N1D and to verify the genus 1 mirror symmetry. This line is left-hand side equals right-hand side. So it turns out that at that 10 years ago that people were actually asking about what's the corresponding mathematical structure that corresponds to BCOV all genus structure predicted by physicists. I would skip the mirror map and let me skip this. I don't have enough time. So for people who are familiar with this, these are Gimentao's notations about the coordinate change of mirror map. Now, besides using BCOV's all genus structure, Huang Mingxin, Albrecht Klemm, and Quankenbusch obtained all genus less than or equal to 51 numerically. in SI, it had seemed impossible to deduce a similar statements for all FG mathematically. Okay. Now, let me state BCOV Feynman rule in a quick way. So there are three kinds of edge. Each of them are indexed by solid, or solid dotted, or dotted edge, denoted by T5, T5, and T. And for each vertex, it will be indexed by a genus and some kind of solid insertions and some kind of dotted insertions. So say n many solid insertion and n many dotted insertions. Anytime such information, we will provide a series called PGMM, exactly counting genus G Riemann surface of degree D, all degrees sum up with m and n insertions conditions. So the condition is that solid line means that you require the Riemann surface has a marking passed by a hyperplane in the quintic. And then the dotted line means that you impose, you require the Riemann surface some kind of tangentially should touch the hyperplane called ancestor class. So notation-wise, PGMA is just counting Riemann surface with so many insertions, n many solid insertion and n many tangency insertions, and then you actually sum up all the degree and form the generating series. That's the PGMM. So this is a series, and assigned to each vertex. And then you, roughly speaking, this m and n are actually redundant. You can use some axiom to reduce them all the way back to FG. To genus G counting Riemann surface series. So these three are essentially the same one. If this is the first time you see it, you don't need to bother what they are exactly. Now the rule says that if you draw all the possible total genus 2 graph, for example, one vertex with genus 2, then you assign it P2, genus 2's counting Riemann surface in quintic. If you pick up another graph, two vertex like this, each of which has genus 1, this is a solid edge, so you assign T5, which will be stated later. And for these two vertex, you insert genus 1 with one solid insertion, the other one genus 1 is one solid insertion. And then you sum them up. So this is a loop, genus 1 with a loop, and then this is genus 1 with two solid insertions, and this loop is a solid edge. Now the total number of graphs are this, and their sum will be a small function in a variable Q. And according to BCOV's argument in 1983, this is going to be a very small informations of polynomials, not too much information. Each of them is a series in NGD, D runs over all the degrees. There are infinitely many unknowns. Now this actually provides an algorithm. If you know all the genus 1 story, P1, P11, P12, all these things, everything in the right-hand side of this plus is known. And if you know a little bit of this beginning informations, then you can determine genus 2. So that will provide a genus inductive algorithm to determine all genus potentials, PG. So follow up the BCOV's Yamaguchi and Yao using, they go through the detailed B-model geometry, and let me skip this as well, just try to highlight that in B-model, they calculate out using the periods and their associate generating series. This can be restated using variational structures, but let me not do that. So you can cook up the certain series in the B-model coordinate Q, and the big X is just a rational function in Q. And other than big X, all the other fours are spatial analytic functions that are transcendental. And these are spatial functions in B-model, and Yamaguchi and Yao solved the differential equations of BCOV. I think BCOV solved it, but they pick spatial frames and to obtain the edge contribution, the solid edge, solid dotted, and dotted. So they pick a choice of this series. So these are very specific series in the B-model quintic modular space. So what that tells us that from the equation we just see, as long as you know this small f2 is a polynomial in big X of degree bounded, then you can determine this genus 2 series simply by first of all, induction tells you genus 1 information of this P11, P12, and Yamaguchi-Yao's formula tell you the age, the propagator T55, all in explicit formulas. So everything from here to the right hand side are known. And a small f2 only involve is a polynomial of degree 3, using a single variable, so there are only 4 numbers for you to determine if you want to determine genus 2 all degree informations, contents. And then all degree information will be in turn be determined as long as you know you lock and find out 4 beginning informations. That's genus 2 degree 0, genus 2 degree 1 up to genus 2 degree 3 counting curves, which can be in turn determined by Gobakuman-Wafa theory. That's another story. So this is a procedure that in VCOV's 93 paper suggesting the genus 2 series may be determined in this way. And they did it. So the Feynman rule in mathematical context, because in A model the Gromov series is determined very rigorously after some trick that we don't really touch path integral, but instead we bypass the path integral major defining problem, and we try to define it using some other method, and therefore FG becomes rigorously defined, and therefore the statements about the VCOV rule become a conjecture, because the argument in V model doesn't work because the path integral are not available yet, even now. So FG, if you do the Feynman sum, then that will become a polynomial in single variable. Okay. And that involves 3G-3 unknowns to determine all infinite many degree possibilities. And there are many consequences of these conjectures. So the genus G partition function will be in this spatial ring defined by Yamaguchi and Yao. And you can differentiate against one of the variable because it's transcendental independent, and you get some kind of genus reduction formula called Yamaguchi-Yao functional equation. A direct, very nice consequence is that this infinite power series converge near q equals 0. It has positive analytic convergence radius. All this was open for 30 years, and the analytic conjecture was never known for any compact Calabi-Yau 3-4. For non-compact Calabi-Yau 3-4, usually you have very simple method to calculate everything. The number can be determined in very direct formula. So let me skip this. So now it becomes a theorem. So in 2018, we proved by myself, Guo Shuai and Jun Li in Fudan Math Center, Guo Shuai in Beijing University. So the Feynman rule with degree bound holds for all quintic Calabi-Yau 3-4s. And this is an extension of also our work in 2021 published in Annals, that the polynomial structure, which means the Yamaguchi-Yao's polynomial ring, contain the FG. The idea is to use a newly arised theory called the mixed spin P field. It has very deep relation with the gauge linear sigma model of Witten, in which the parameter has to become a dynamic field in here. So in Witten's work, gauge linear sigma model, the Fayette Iniopoulos operator is a parameter of the theory, is an index. And now in this theory, this becomes a field, a dynamic field that you need to integrate over and contribute. So it follows a series of works by Guo Shuai, Yonghun, Junli, Wei Ping, Melissa, and Zhou Jie, and also we'll have other stories. Okay, wonderful. I use 15 minutes. So let me try to speed up to give you an extremely rough idea of the picture about MSP theory. So how come the counting of Riemann surfaces will satisfy this kind of Feynman rule? So the idea is that you don't look into Calabi-Yau. You need to extend the Calabi-Yau into higher dimension. Calabi-Yau is 3-4. You need to look at 3 plus any big number dimension and look at the curve in this extension. So you take a cone over quintic. So this is P4, and inside of which you say this is a hypersurface quintic. You pick one point outside P4. You connect this point with any point on the quintic by straight lines. Then you get a cone. So this cone can be described by one single equation in CP5. So you get one additional coordinates. So I will try to draw this to mean that I have additional point O outside P4. So this can realize the quintic cone as a quintic hypersurface in P5. Now a wish is that you count holomorphic curves, higher genus map to this quintic cone. Now the quintic cone it is in CP5, but the degree is not 6. It's not Calabi-Yau. The degree is not 5 plus 1. So the counting of curves in the quintic cone, it looks like a Fano variety. And if you don't put insertions, the counting is 0. Now a different way to look at counting curves to here, because you have this direction C star action. So you will have high genus curve mapped to quintic, maybe all the whole genus map to quintic, or then that will contribute PG. Or you may have there's a genus 1 curve mapped to quintic, and then connected by a P1 to there, and another P1 back, and then another genus G2 curve mapped to quintic. So that would be PG1, PG2 individually, and this P1 into and outside provides you a propagator. It looks to be very, kind of a coincidence that fit into the Feynman structure proposed by BCOV. But there are technical issues. So, I mean, this provides your identity. It looks like BCOV's statements. Is that if you try very hard to calculate this propagator, you will find out that it doesn't really match BCOV. It matched to some degree. It matched to some degree. It looks crazily bad, but it's almost there. So this is the idea. Yeah. Now there are about some problems about this idea. The issue is that quintic cone is singular. You cannot count Gromov-Witten. Even the passing group cannot be defined. It cannot. And so realize everything is by Landau-Ginzburg model. So that will bypass this issue. The cure is that you realize the quintic manifold as the critical loci of this KP4. And then you realize this extended quintic cone also as a critical loci of some Landau-Ginzburg space. You look at KP5, and this will give you the way. So this is the P4, the boundary is P4. Inside the blue disk is the P5. The vertical green is the canonical boundary of P5. And then the quintic cone is here, the red one. Now the total space of KP5, over which you have a holomorphic function, this critical locus will be, quintic cone with a union with one line, which is P1. This is P1. An additional funny P1, yeah. So somehow for people who want to see Gage-Neal model, all the face in one picture, this is the picture, the master space, including KP4, and the yellow part is the Landau-Ginzburg C5 mod Z5. Okay. And then you count curve in here. Now you can do some partial compactification, and the W will be compactified. So because you always want critical loci to be compact, but this purple line is not compact. Okay. But you can do some compactification. And then after that, then counting curve mapped to the previous picture will become a mixture of spin curve with a P field. Because if you have curve maps to the yellow part, you will analyze the geometry will give you a spin curve, which means that it involves a line bundle that is root of canonical line bundle on the curve. Okay. And the P field will govern the curves living on the green direction. And if it is on the yellow direction, it gives you spin. So you will have P field provided from the green and a spin from the yellow. And these are the additional, mathematically additional ingredients other than those curves that really maps to CP5. And that's why we call it MSP, because it mixed up the newly arised subject called spin and P field, which comes from we further geometrize more physics theories. So counting curves in the quintic cone, as I said about the wish, will be realized as the MSP field. And after the theory, the wish will become true, but you need to do one thing, that is to make the propagator, that the curve travel to all and back to give you the propagator, you need to raise it to n-dimensional extension. That is, so maybe no, I don't need to, I have a picture. So that's it. So quintic, you add 1 point and you connect it. Now actually you need to do 2 points and 3 points and 4 points. They are actually a CPN extension of the quintic cone, and you count curves. And that will give you BCOV formula. Okay, so let me skip this. So BCOV formula actually comes from here. You have genus 3, the total integration is 0, and you may have genus 2 here, and this gives you propagator. This is genus 1, and this is the other non-separating case. And the curve that travel away from quintic and get inside the secret extended dimensional project space and come out, those as long as you make the project space into arbitrary high dimension Pn, that will give you exactly the same formula of BCOV propagator. And I don't know why. I don't know why. Yeah. So I hope I will know why before I quit. Yeah. Okay. So yeah, to take too much time. Okay. So BCOV Feynman rule in A model will be MSP Feynman rule. Okay. So this is the technical part. So roughly to describe the space I mentioned in the picture, These are the coordinates x and p, and these are the quantization. These are the Kähler parameter. That after you want to consider the geometry, you make every field, every coordinate become fields. That is sections of Lamb bundles over Riemann surface. That's a worksheet. And then the Kähler parameter, you also make it become fields. That is sections of Lamb bundles over Riemann surfaces. And this is the ideas of Wei Ping and Jun Li. And then the whole thing admits a enumerating theory. And then there are two numerical numbers, that is the degree of these two, U1, U2, which we call D0, D infinity. The picture is quite easy. I will tell you later, but I need to highlight that the geometry says that before, in the beginning, we talk about extension by 1 point. Now I talk about I need to extend by many points. Actually, big N, many points. This big N will be correspondingly imposed here. And that is for the Gromov-Witten series BCOV. But if you want to do it for the Landau-Ginzburg series, FGRW series, then you need to put big N in the other side. Okay. So I will talk about that. Okay, so D0 is the curve intersection number. You imagine you have a curve. The curve will touch the green wall, the side cylindrical wall. The intersection number with the curve will be D0. D infinity will be the intersection number of the curve with the yellow cap, which is also a divisor. Okay. Now, if you are counting curve in quintic, this is the quintic Gromov-Witten to start with. Now, it is embedded in a huge theory, and in this theory, another phase is also there, counting curve inside the yellow ones. By selecting suitable degrees, like for example, demanding that the curve you want doesn't touch the yellow ceilings, then you are actually looking at curve actually comes from quintic cones and somehow here, but it doesn't touch ceiling, so it is inside here. That will give you Gromov-Witten theory and BCOV here. On the other hand, if you try to look at curves that you require not touching the blue ones, not touching the green wall, green side wall, but only the curves that will map to this purple line, then you will obtain a structural result governing the Feynman structure of counting curves of the Landau-Ginzburg model, the FGRW invariance. Let me talk about this here. So a fine Landau-Ginzburg model, that's the goal I want to say today. So I will try to speed up, I don't have too much time. So the yellow ceiling I just draw is actually this, C5 mod Z5 with a potential. It's a special Landau-Ginzburg space called quintic singularity. So we can suggest that theory enumerating curves in here give you somehow enumerating curves in quintic Calabi-Yau threefold. But the transformation between these two theories called Calabi-Yau Landau-Ginzburg correspondence is not qualitatively written down. Yongbin Ran is trying to do this, but I don't think it is finished yet in Yongbin Ran's work. So we can talk about that later. Now, let me spend some time on this. So the theory actually is of very interest, and I do hope this has certain other link to other subjects because it makes the whole thing more linear. The space is the module is the genus G Riemann surface with a Lamb bundle which is a root of canonical bundle. And it can be easily compactified. So you put moduli space and you put 1/5 to mean that you include a spin bundle. This is called a 5 spin. Now there will be a way to associate a enumerative curve class in here. This is a virtual class in here. There are many stories about this, but some keyword may be related. If you're interested, it will be related to the Hamiltonian floor theory. Actually, predicted by Flower 30 years ago, even before Witten. But this is a higher genus version. Now, so you need to perform some higher genus trick by Witten. Now, only when this numerical thing is satisfied that the cycle is non-trivial, and it's called Witten top chain class. It's essentially counting curve in the yellow ceiling. Now, count the degree, like NGD, you have theta GK, so it will be an analogy of the genus G degree K Gromov-Witten invariants. These are called fine Jarvis-Run-Witten invariants. The analytic theory, the Kranich model is written by fine Jarvis-Run a while ago, I guess 15 years ago. Yeah, but there are a few different constructions which are not consistently checked, agreed yet. Now you can formulate generating functions just like what you did in Gromit theory. And then by using the MSP picture, the picture I gave you with a lot of colors there. So by similar treatment, my student Zhang Huaigong, I think just a few days ago, showed that this FGRW, Landau-Ginzburg generating function, is an analytic functions nearby the origin, nearby the Gepner points. So this proved the analyticity of Landau-Ginzburg theory for the first Calabi-Yau type singularity. It's a singularity invariance. A little bit more detail, just these slides. So there's an I function simulating the Gimenthaus ones, and these 5, 1 over 5, 2 over 5. These 4 copy of phi are the states. Coefficient are the I functions, and the mirror theorem was proved by Guoshuai and Ross. And everything is similar to the quintic case in many sense, but something is different. But the idea is that there are generating functions expanded nearby the Gepner point, and Zhang Huaigong showed that Fg will be in a polynomial ring. Not to the optimist prediction, but this is proved. Okay, so everything detail is checked. So somehow the statement about the singularity was nearby the Landau-Ginzburg point, that is t equal to 0. Yeah, it's not very important. Yeah. So let me try to skip this, but I just want to highlight that in the MSP formulations, if you want BCOV for quintic, you put large N here, and now you put large N on the Kähler parameter for the curve, positive Kähler parameter. Now you put large N for Zhang Huaigong's case. You put large N on the Landau-Ginzburg Gepner near the coordinates. Lambda corresponds to it. Yeah. So that's the idea. So as I said, you choose curve maps to the purple line, and then curve maps to this point give you FGRW. Curves map to here and P1 to here and back and here and back. Travel from here and travel and come back, give you the propagator. And then the idea is similar. The remainder thing is calculation. And still we don't know why. So we calculate much faster than we understand. So that's the experience I got for now. Yeah. So thank you. Okay. It's why it is particular. They need to use some other prediction, some other conditions to lock down the to determine the FG, and those can are only available when they take intersections for the available G's. They needed genus less than or equal to 51. They can move a little bit forward, but not universally. Yeah. Yeah. Other questions?
谢谢介绍。今天在场的都是中国人，所以我就一半用中文，一半用英文吧，好吧？这个 talk 里面我要介绍一个，好吧？In this talk, I would like to give an introduction of the history developments in the theory of 所谓的远阿贝尔几何，是吧？就 curve 的远阿贝尔几何。然后 additionally, I will discuss a joint work with Zhi Hu and Yang Yu about the unabelian phenomena of curves over algebraic closed field of characteristic p bigger than 0. Yeah, in the 1980s, in his letter to Fartings, Grothendieck suggested a theory of arithmetic geometry which he called unabelian geometry, 就远阿贝尔几何，是吧？ This theory mainly focuses on the following question: how much geometric information of an algebraic variety over a certain field can be carried from its algebraic fundamental group? 当然，这里的 fundamental group 我们可以要求它是 entailed 或者 termed 都可以，是吧？那 moreover, an algebraic variety over a certain field is called unabelian by Grothendieck if it can be determined completely by its algebraic fundamental group. And to classify the unabelian varieties in all dimensions over all fields is called unabelian dream of him. At present, we don't know what unabelian variety exactly is in general. In general 我们不知道，但是我这里可以写一个东西，它是 unabelian 的。就 dimension 1的时候，hyperbolic curve is unabelian. OK， 那这个 talk 里我们基本上都是考虑 curve。And in a particular case of one-dimensional schemes, roughly speaking, Grothendieck's unabelian conjectures are various formulations based on the following unabelian philosophy. And I will state the home version of this philosophy. And we also have Ising version and a weak Ising version. And the home version is the strongest version. The set of dominant morphisms for hyperbolic curves, e.g., non-singular projected curves of genus at least 2, can be determined group theoretically by a set of open continuous homomorphisms of the algebraic fundamental groups. Namely, we have the following bijection. The left-hand side is non-trivial morphisms of curves. The right-hand side is open continuous homomorphisms of fundamental groups. If the base field is a number field, then it can be regarded as a non-abelian analog of the Tate conjecture for divisors on abelian varieties. And this is proved by Fartings. Let me explain this a bit. We let A, B be abelian varieties. Abelian varieties over a finite field. Then we have anamorphism AB tensor with QP equal to anamorphism over G of TPA, TPB tensor with Q. And this is called a Tate module. And we consider the geometric fundamental group. They are pi 1a equal to the product over OP of TPA. Yeah. So for one-dimensional scheme, we can use the analog. We replace TPA over O product with pi 1a. And we ask whether the endomorphism between one-dimensional schemes can be determined by the morphism between their pi 1. Yeah, that's the analog. But here I have to say that abelian varieties are not an abelian variety. So this is just analog in philosophy. Now, in particular, Hom version implies the following. As I said, we have Ising version and a weak Ising version. The Ising version says that the isomorphism of curves has a bijection with isomorphism of fundamental groups. The weak Ising version it says that if there is an isomorphism of curve, then there is an isomorphism of fundamental groups. Yeah, it seems that 第二行只是把那个括号去掉了，是吧？这里没有写清楚，我解释一下。Weak Ising version if x is isomorphic with y, then pi1x isomorphic with pi1y. That's what this really means. And note that we have the Hom version implies Ising version, and the Ising version implies weak Ising version. Yeah. And let me explain some of the most significant results obtained by Shinichi Mochizuki and Akio Tamagawa. And their innovative ideas and techniques have been dominant in the theory of unabelian geometry since the 1980s. So in the part 1, I will talk about arithmetic unabelian geometry. Let K be a field, K bar is algebraic closure, GK the absolute Galois group, and Xi, I for 1 and 2 are hyperbolic curves of type Gxi nxi over K. Here Gxi is the genus of the smooth complication of Xi, and the nxi is the mark point, and we have the inequality 2Gxi plus nxi minus 2 is bigger than 0. And we let pi xi be the etail or 10 fundamental group of xi, and delta xi be the etail or 10 fundamental group of xi base change to its algebraic closure, i.e. this is a geometric fundamental group of xi. And then we have the following fundamentals exact sequence of fundamental groups for suitable choices of base points. That is 1 to the geometric fundamental group, delta xi, then to the algebraic fundamental group, pi xi, and then to gk to 1. The exact sequence above implies a natural outer Galois representation, gk to automorphism of delta xi, and it is defined by the right-hand side. And here the INN delta xi is the 几何基本群的自同构群，是吧？ When characteristics k equal to 0, respectively bigger than 0, delta xi, respectively the maximal prime to p quotient of delta xi is a profinite group which is isomorphic to the profinite completion, respectively the prime to p profinite completion of the topological fundamental group of a Riemann surface of type Gxi nxi. And this is by the Riemann existence theorem, right? Thus, the structure of automorphism delta xi, respectively automorphism of delta xi p prime is known. Now we let Hom the pi xi, pi x2 be the set of open continuous homomorphisms of profinite groups. And we let Hom gxi, pi xi to pi x2 to be those open continuous homomorphism that is compatible with the gk. And it is just a commutative diagram over gk, right? And we note that there's a natural action of delta x2 on Hom gk pi x1 pi x2 via inner automorphisms. When characteristic k is equal to 0, based on the Hom version philosophy mentioned above, we have the following conjecture. It's a Hom version conjecture 1, i.e. the natural map from Hom k dominant x1 to x2 to Hom gk pi x1 pi x2, and the quotient the inner automorphisms of pi x2 is a bijection. Here the dom means dominant morphism. In particular, we have the following two versions based on Eisen version and the weak Eisen version philosophy. Yeah, let's just the other two versions, the weaker versions. The conjecture 2 Eisen version is the natural map Eisen k x1 x2 to Eisen gk pi x1 pi x2 modular the action of the inner automorphism of delta x2 is a bijection. We just replace the home by Eisen here, right? The conjecture 3 is the weak Eisen version. We have x1 over k isomorphic to x2 as k schemes if and only if pi x1 as gk groups are isomorphic as delta x pi x2 as profinite groups such that they are isomorphism compatible with gk. And the above conjectures can be also formulated for curves in positive characteristics by ignoring the effects of forbiddenness. For example, if K is a finite field, for Eisen version, we need to replace Eisen K x1 x2 by Eisen scheme x1 x2. We just we consider a set of isomorphisms as schemes. But in fact, Grothendieck only formulated his conjecture for curves over number fields. The first is over the fundamental of base field K. No. It is isomorphism as schemes in general. Yeah, it's just isomorphism as general schemes. It doesn't have to preserve the base field. If K is a number field, the weak Eisen version was proved by Nakamura when gx1 and x2 equal to 0. And the Eisen version was proved by Tamagawa by using class field theory and algebraic geometry in positive heuristics when xi is affine, and by Mochizuki in general by using log geometry and Tamagawa's result. And moreover, Mochizuki, by an invention paper, obtained a very strong result. Using Farting's p-adic Hodge theory, he proved the home version when K is a sub-p-adic field, i.e. a field which can be embedded as subfield of finite generated extension of QP. 当然，这个就包括了所有的 number field， 是吧？那 Mochizuki result is one of the most highest achievements of unabelian geometry， 是吧？因为这个 sub-p-adic field 非常多，就包括了很多 field。And since mid-2000s, the development of Grothendieck unabelian geometry in arithmetic field of characteristic zero mainly focus on the following topics. The first is absolute unabelian geometry. Roughly speaking, this theory focuses on reconstructing a base field for arithmetic fundamental group of curves. So for algebraic number field, we have Newkirch, Wuchich and 什么人？你们知道那个名字吗？这不会读。Wuchich Newkirch-Wuchich 定理就是 K1 isomorphic to K2 当前紧张 GK1 isomorphic to GK2。但这个只对 number field 是对的，是吧？但是对p-adic local field 这个定理就没了。那现在呢，我们就可以考虑 pi x1 K1 同过于 pi x2 K2 K 导出 GK1 同过于 GK2， 这个对 local p-adic field 就对了。是吧？这里 K1、K2 都可以是 GP 的有限扩张，这是第一个情况。那是 mono-unabelian geometry. Roughly speaking, this theory focuses on giving a group theoretical algorithm for reconstructing schemes from fundamental groups. And we also have so-called combinatorial unabelian geometry and its application to Grothendieck-Tensmuller theory and higher dimensional unabelian geometry. For example, a configuration spaces. Roughly speaking, this theory focuses on reconstructing singular structures of pointing stable curve from log E-tail fundamental groups. Yeah, and all of the above topics were developed primarily by Mochizuki and with his students. If K is a finite field, the Einstein version was proved by Tamagawa when Xi is affine. Moreover, Mochizuki extended Tamagawa's result to projective case. If K is a field finite generated over a finite field, Einstein version was proved by Jacob Stix by using Tamagawa and Mochizuki's results. But on the other hand, at present, the following two important cases remain unknown. In positive characteristic, no result is known for home version. And nothing is known if K is a local field of characteristic P equal to P bigger than 0. And since mid-2000s, the development of quadratic Abelian conjecture in a respective field of characteristics P mainly focus on the following topic. If Abelian conjecture via small fundamental groups, as I mentioned above, the original form of quadratic Abelian conjecture says that Xi can be determined by the outer Galois representation Gk to automorphism of delta Xi. However, in positive characteristics, the geometric fundamental group delta Xi is completely unknown, and then this topic aims to prove Abelian conjecture by replacing delta Xi by using certain small quotient of delta Xi, which has simple structure. And I just mentioned the following important results. When K is a finite generated over Fp, the weak Einstein version can be proved by replacing delta Xi by the following. The maximum prime to P quotient, delta Xi P prime. And we recall that delta Xi P prime is isomorphic to the prime to P completion of the topological fundamental group of Riemann surface of type Gxi Nxi, and is represented as above. All of the above topics were developed primarily by Tamagawa and written with Said and his student Yamaguchi. And as I mentioned above, the structure of automorphism delta Xi is known. The quadratic Abelian conjecture says that over arithmetic fields, geometry can be controlled completely by the highly non-trivial outer Galois representation Gk to outer automorphism delta Xi, reviewed above. For example, good and stable reduction criteria, p-adic Hodge theory, Weil conjecture, and the Galois cohomology, etc. Namely, the Galois actions play a central role for an Abelian geometry over arithmetic fields, and we have geometry equal to the top geometric fundamental groups plus Galois actions. And roughly, it means that geometry is equal to topology plus Galois action. For more details on Abelian geometry, in particular, quadratic Abelian conjecture of curve or arithmetic field, we refer to the following three papers. Yeah, if you want a detail of the papers, you can come to me after the talk. And then we go to part 2, beyond arithmetic. We will talk about Abelian geometry of an algebraic closed field of characteristic P bigger than 0. It is also based on Grothendieck's Abelian philosophy, but Grothendieck didn't think about it by himself. And next, I want to explain Tamagawa's discovery about Abelian geometry of curves over algebraic closed fields of characteristic P. And here's the setup. Let X be a smooth projected curve on an algebraic closed field K of characteristic P equal or bigger than 0 of genus G, and dx a finite set of closed point of X of cardinality n. If P equal to 0, for example, K is the complex field, the Italian fundamental group of X minus dx is isomorphic to the pro-finite completion of the topological fundamental group of the Riemann surface. Yeah, and the analytification of X minus dx, and namely is represented by the following. So the structure is well known and depends only on Gn. But if P is bigger than 0, the situation is completely different from that in characteristic 0. Although Abianca has famous conjecture proved by Reynolds and Habata, shows that the state of finite quotients of Italian fundamental groups of affine curves can be completely determined by Gn. The structure of Italian fundamental groups are very mysterious and no longer known. Yeah. Bianca's conjecture only reveals the tip or iceberg of mysterious of the fundamental groups of curves in positive heuristic. Now, in 1996, Tamagawa discovered surprisingly that there exists an abelian phenomena for curves or algebraic closed field of positive heuristics. What does this mean? This means that the geometry of curve can be possibly determined by their geometric fundamental groups. This means that we don't consider the Galois actions, since the Galois curve of base field here are trivial. Namely, we have geometry is completely determined by the geometric fundamental groups, i.e. the geometric fundamental groups in positive heuristics contains high enough information, very non-trivial information. This kind of abelian phenomenon is quite different from that of arithmetic fields, and it is the reason that we do not have an explicit description of a tail or tan fundamental group of any hyperbolic curve in characteristic P. And based on Grothendieck's abelian philosophy mentioned above, in his paper Fundamental Groups and the Geometry of Curve in Positive Heuristics, Tamagawa made a conjecture world concerning ETAL and tan fundamental groups of smooth curve over algebraic closed field of positive heuristics. And more precisely, he successfully formulated the so-called weak Eisen-Wolfson conjecture and Eisen-Wolfson conjecture for curves over algebraic closed field of characteristic P bigger than 0. And at present, all of these conjectures are still wide open. And I will mention some special case that is known. For the case of smooth curve, the following result is the only result which we know about the weak Eisen-Wolfson conjecture. And at present, nothing is known about the Eisen-Wolfson conjecture. This is the result by Tamagawa. Let xi, I belongs to 1 and 2, be a hyperbolic curve of type 0n. I mean, we only consider genus 0 case. Or 1, 1, or the simplest elliptical curve case of fp bar and pi xi, the tan fundamental group of xi. Then x1 is isomorphic to x2 as strings, if and only if the isomorphism between their pi xi and pi x1 and pi x2 is non-empty, where isom pi x1 x2 denotes the set of isomorphisms of profinite groups. Then, while the weak Eisen-Wolfson conjecture remains a wide open problem for an arbitrary type Gn, Tamagawa has achieved an important result known as the finiteness theorem. He says that over fp bar, only finitely many isomorphism class of hyperbolic curve have the same tan fundamental groups. This is what he proved. This is the general result we know. And this result is one of the highest achievements in the theory of abelian geometry. And it is included in the new edition of SGA1, right? As one of the most important results since Grothendieck introduced the ETAL fundamental groups. And all the results obtained by Tamagawa mentioned above were generalized to the case of arbitrary, possibly singular pointed stable curve by Yang using his development of the so-called combinatorial and abelian geometry in positive heuristics. Now we go to the part 3 of this talk. It is beyond arithmetic. We talk about an abelian geometry of an algebraic closed field of characteristic P bigger than 0, based on the philosophy of moduli space of fundamental groups. And this is what we do in our paper. Right. In the remainder of this talk, I will explain a new kind of abelian phenomena that exists in the world of positive heuristic and that cannot be understood by using Grothendieck's original abelian philosophy, i.e. the home version mentioned above. And so first we recall that Grothendieck abelian philosophy concerning home version is that non-trivial morphisms of curves have a bijection with open continuous homomorphisms of fundamental groups. Then we have the following natural question. Can we formulate a home version conjecture for tan fundamental groups of arbitrary hyperbolic curve in the case of algebraic closed field of characteristic P bigger than 0 by using Grothendieck's original abelian philosophy? The answer is no in general. So roughly speaking, we have the following phenomenon. Let Ki, I belongs to 1 and 2, be an algebraic closed field of characteristics P bigger than 0. Then there exists a hyperbolic curve Xi over Ki, such that the dominant homomorphism between X1 and X2 is empty. But the open continuous homomorphism between pi x1 and pi x2 is non-empty. Here, pi xi denotes the 10 fundamental group of xi. And this means that we cannot formulate a Hermitian conjecture in general by following Grothendieck's original suggestion, since we don't have the following isomorphism. But does the above example indicate that there is no abelian explanation, i.e. corresponding geometric explanation for the group theoretical object, the open continuous homomorphism between pi x1 and pi x2 in characteristics P equal to 0, bigger than 0? Yeah, in fact, we have observed that open continuous homomorphism between pi x1 and pi x2 contains deep information about the topological structures of modular space of curves. It is the first abelian phenomenon that cannot be explained by using Grothendieck's original abelian philosophy. Yeah, it is what we observed in our recent paper. Here, the topological structures means the Zariski topological structures. Our main result is as follows, which generalizes the result of Tamagawa concerning the weak isolation conjecture mentioned above. This is our theorem 1. The result of me with Hu and Yang. Let xi I belongs to 1, 2 be a hyperbolic curve of type 0n or 1, 1 over fp bar, and pi xi the 10 fundamental group of xi. Then x1 is isomorphic to x2 as schemes if and only if the open continuous homomorphism between pi x1 and pi x2 is not empty. And note that our result is completely different from that of Tamagawa, and it cannot be deduced from Tamagawa's result. The reason is the following. We do not know whether or not isom pi x1 and pi x2 is not empty if the open continuous homomorphism between pi x1 and pi x2 is not empty. And in fact, a highly non-trivial result of Tamagawa says open continuous homomorphism between pi x1 and pi x2 is non-empty, and isomorphism between pi x1 and pi x2 is empty in general. On the other hand, our result has a completely new and abelian philosophy that is essentially different from that of weak isolation conjecture. Let me explain it by using a theory called the modular space of fundamental group introduced by Yang.
Can you just say the statement again? Why?
Which statement? This?
No. So we do not know whether or not. So okay. So if there's an open homomorphism, right? Then Tamagawa's result tells you that they're isomorphic. That the curves are isomorphic.
It means in general, there are not isomorphism between pi x1 and pi x2, but there are a lot of open continuous homomorphism between them.
Right. It sounds like your result is stronger than Tamagawa's result. Right?
Of course. Right. That's why we publish it. Yeah. Let MGN bar be the coarse modular space of pointed stable curves of type GN over FP bar. And MGN belongs to MGN bar, the open subset corresponding to smooth pointed stable curves. And Q3 belongs to MGN bar, an arbitrary point. Let KQ an algebraic closure of the residual field of Q. Then we consider SQ data equal to SQ DSQ, the pointed stable curve corresponding to spec KQ to MGN bar. Then SQ denotes where SQ denotes the underlying scheme, and the DSQ denotes the set of marker points. Note that SQ minus DSQ is hyperbolic when SQ is non-singular. And pi Q, the admissible fundamental group, or equivalently log ETL fundamental group of SQ data. Note that if Q belongs to MGN, then pi Q is the 10 fundamental group of SQ data. And let Q belong to MGM bar and pi Q the admissible fundamental group of pi Q delta. We put the following. Let pi AQ be the set of finite quotients of pi Q, and pi GM bar defined to be the set of isomorphism classes of pi Q. Here Q belongs to MGM bar. And then we have a topological space, pi GM bar, O pi GM bar, which I call the modulus space of admissible fundamental group of type Gn, whose underlying set of is pi GM bar, and whose topology O pi GM bar is the topology which is generated by the open sets UG. Q belongs to pi GM bar and G belongs to pi AQ, where G is an arbitrary finite group. We still use the notation pi GM bar to denote the topological space pi GM bar, O pi GM bar. Moreover, by introducing the so-called Frobenius equivalence on pi GM bar, one can prove that there exists a continuous map between the topological spaces pi GM admissible from MGM bar defined to be MGM bar and Huaxie the MGM bar defined to be MGM bar quotient the Frobenius equivalence mapped surjectively to pi GM bar, Q mapped to pi Q, where the topology of Huaxie the MGM bar is induced by the Zariski topology of MGM bar, and the Q denotes the equivalence class of Q, and the pi Q denotes the isomorphism class of pi Q. The main conjecture of this theory is the following. The pi GM admissible from Huaxie the MGM bar subjectively to pi GN bar is a homeomorphism. 这里是吧？作为拓扑空间是个统胚。This conjecture tells us how to consider an abelian geometry of curve of algebraic closed field of characteristic P, namely, the abelian properties of curve or algebraically closed field of characteristic P are equivalent to the topological properties of pi GM bar, i.e., all geometric properties concerning the topology of MGM bar should be abelian. And we note that the weak Eisen-Wolfson conjecture only says that pi GN admissible is a bijection as sets, not a homeomorphism. And until the homeomorphism conjecture since 1996, the unabelian phenomena related to the weak Eisen-Wolfson conjecture are the only unabelian phenomena that we know for curves of algebraic closed field of characteristic P. And the current state is the following. The good news is that by using the homeomorphism conjecture, many new unabelian phenomena can be seen, and many open problems and conjectures can be formulated. But the bad news is that almost all of the open problems and conjectures concerning pi GM bar are much more difficult than the finiteness theorem. Now then, our main result implies the following important result. The homeomorphism conjecture holds for one-dimensional modular spaces, i.e. for M0n bar and M11 bar. And we note that Tamagawa's result only says that the coarse modular space of M04 respectively M11 can be reconstructed grouped theoretically from pi 04 respectively pi 11 as sets, i.e. pi GN admissible is a bijection as sets. 就Tamagawa 就证明了这是一映射，是吧？然后另一个人Yamaguchi 证明是连续映射，那我们的主定理就证明这是个闭映射，这是我们主要做的。This result is reminiscent of a famous theorem in the theory of classical Teichmüller spaces, which states that the Teichmüller spaces of complex hyperbolic curve can be reconstructed group theoretically from the spaces of discrete and faithful limitations of topological fundamental groups of underlying surfaces into the group PSL2R. 那我们主要用的工具是什么呢？ We use the formulas concerning p-average and maximum generalized Haswell invariance, or p-rank, associated to The main tools are following. The formulas concerning p-average and the maximum generalized Hauswell invariant, or p-rank, associated to prime to p coverings proved by Tamagawa and Yang using the so-called Runhong-Tamagawa set divisors. Roughly speaking, the formulas can be regarded as the rules of weight theory in the case of arithmetic fields. For example, Weyl conjecture, p-adic Hall theory, and by using the formulas, we can reconstruct various invariants associated to point stable curves. For example, topological rank of a dual semigraph, genus, cardinality of set of mark points. And let K pt minus 1 defined to be the following kernel. And we put the average p pi q to be the right-hand side. For example, in a simple case where SQ dot is non-singular, the formula of p average or p rank is the following. If n equals 0, the limit for t go to infinity is g minus 1. If n is not equal to 0, it is g. And the theory of combinatorial and abelian geometry in positive characteristics developed by Yang. Roughly speaking, this theory allows us to treat an abelian geometry of a singular point stable curve by using results of an abelian geometry of smooth point stable curves. Yeah, then that's all of my talk. Thank you.
So what is the main difficulty to generalize your approach to higher Chinese curves?
And the method, our method is completely very specific to genus 0 and 1. And for general high genus, we don't have any idea. Yeah.
But do you expect the same kind of conjecture both?
Yeah. 题目是 Displaced and p-divisible groups。我们欢迎。
谢谢介绍。然后，我今天要讲的是那个 Displaced and p-divisible groups。我的那个中文比英文好一点，如果我用中文讲，可能很快就讲完了。我还是用英文讲。然后 ，Yeah, so I think most of us heard about p-divisible groups, but maybe not displaced. I will first review the basics of these objects, and then especially the classification result of think and law, and then I will explain one of the applications. So I'll start with the following setup. For us, R is a commutative ring with 1, and near R is a category of nilpotent R algebras. A formal group over R from Grothendieck's point of view is a factor G from near R to the category of abelian groups. So it satisfies the following three either conditions. So it sends 0 to 0, it respects the short exact sequence, and it commutes with infinite direct sums. The Lie algebra of a formal group is defined to be this thing. So it's the value of this G on epsilon R. So we give this R a new algebra structure such that the multiplication is trivial. So this Lie algebra is an R module in the canonical way. If we have two formal groups, a morphism is called an isogeny if they have the same dimension, and the kernel of this morphism is representable. And finally, we say a formal group is p-divisible if this morphism here is an isogeny. So yeah, the kernel of this thing is a group scheme. So in terms of power series, from a more concrete point of view, a formal group G over R is represented by this sphere of this ring of power series, and a morphism between two formal groups is an isogeny if we look at the map between these two rings, and we require that this yi is nilpotent in this quotient. So in both cases, it is difficult to check whether this phi is an isogeny. So these things are kind of abstract, and we would like to give a classification for these objects. And I think the most successful ones are given by Cartier theory and the Dieudonné theory. So what is Cartier theory? So now we focus on the local case. We let R be a ZP algebra. We define this AR to be the algebra generated over WR by two operators, F and V. So this WR is the ring of Witt vectors. Yeah, I think we saw this yesterday morning. So these two operators, F and V, satisfy the following four conditions. So this AR is not commutative. So VAF equal to this thing. So this small v and small f are Verschiebung and Frobenius of this ring of Witt vectors. Now we have this AR. We define some kind of combination of this thing. So inside VAR, we have these right ideals generated by V to the L. And these ideals induces a topology on this AR, and we define ER to be the inverse limit of this quotient. It's kind of combination. And this ER is the famous Cartier ring. A Cartier module is nothing but a module over ER. And the Cartier module is called reduced if it satisfies the following three conditions. So this V is injective, this M is somehow complete, and this quotient is a finitely generated projective R module. Okay, we have all these definitions, and we have the following main result. So the local Cartier theory says the following. If we have this R, and then the category of formal groups over R is equivalent to the category of reduced ER modules. And this equivalence is somehow very explicit. If we define this W hat to be this functor, it's a subfunctor of this functor of ring of weight vectors. So we require the coordinates to be 0 when this T is large. And then one can show that this ring of this Cartier ring is isomorphic to the endomorphism algebra of this W hat, of course with opposite multiplication. And then let G be a formal group over R. We can consider this home from this functor W hat to the functor G. And this is certainly a ER module in this sense. So this basically is the construction of this equivalence. In general, isogeny is not easy to characterize explicitly by these Cartier modules. So we have these formal groups, but we don't know. So under which conditions on these Cartier modules, these formal groups are p-divisible. But being an isogeny is a property stable under base change. So we can consider a morphism phi between two formal groups and the modular prime ideals. And then we get into characteristic P world. So then we have more tools. So that's where we have Dieudonné modules. So now we let K be a perfect field of characteristic P. A Dieudonné module over K is a special Cartier module, is a free WK module M of best rank with two operators, F and V. So satisfies these conditions. And we say a Dieudonné module is reduced if this V here is nilpotent modulo this PM. And then we have a Dieudonné, we have the following result. So this is the main result of Dieudonné theory. Now in this setting, our K is a perfect field of characteristic P. Then the category of formal p-divisible groups over K is equivalent to the category of reduced Dieudonné modules over K. So one can see the difference here. So for Cartier theory, we classify formal groups. And for Dieudonné theory, we classify p-divisible groups over a field of characteristic P. So this is good. So we have somehow a classification result, but this is not good enough. So we have a very strong restriction on this K. So it has to be a perfect field of characteristic P. So would like to resolve this problem. So one way to do it is to use displays. So I think the idea origins from Mumford and then developed by Zink in around 2000. So what are displays? So still, we let R be a ring. So for simplicity, we assume P is nilpotent in this ring R. A display P over R is a quadruple, so PQFF1. This capital P is a finitely generated projective WR module. This Q is a submodule of P, which is not too small. It contains IP. I is the image of the Verschiebung. And F1 are from Frobenius linear morphisms satisfies the following two conditions. So yeah, we don't have to remember all these things, but we just need to know these are all linear objects or semi-linear objects. So these objects are good in several ways. For example, there exists a decomposition P equal to L plus T, such that this Q is nothing but L plus IT. So it contains IP, and we know, so where this I appears, it appears for this T part. we call it a normal decomposition, and the normal decomposition is compatible with base change. So if we have an arrow from S to R, and PS is somehow a lift of this display over R, then for this PS, its normal decomposition is just the base change of the normal decomposition. And for all this data in here, we put them together to get a structure equation from L plus T to L plus T. So it's a from Bayes linear isomorphism. It is represented by matrix. If everything is free, then this is nothing but a invertible matrix with entries in R. And since the normal decomposition is compatible with base change, if you want to deform a display, you just need to somehow deform an invertible matrix. So, yeah, all these are just linear algebra. So corresponding to this reduced condition, we have a technical condition, so called nilpotent. So if we have a display over R, then we can define the map V sharp. So I think the details is not important. So we have V sharp from P to its twist, and then we can define the twist of this V sharp from this twist to this twist of P. And then we can define the map from P to this from this big twist by this composition, by this identity. So this VM sharp is a composition of all these things. And we say that P is nilpotent if this very complicated thing is 0 for big M, so it disappears. Okay, so before we go to the main result, we need the following construction. So now we have a display over R. We can define some functors from this near R to a Abelian group, the category of Abelian groups. So starting with this P, we define the functor B hat. So it's basically the tensor product of W hat and this module. And then we can define the Q hat to be the kernel of this thing. One can see that the kernel is generated by two types of elements. So the first one comes from W hat to N. The second one comes from P to the quotient. And from this observation, we can define the transfer between this Q hat and P hat. So we can just define the transfer on these generators of this Q hat N. Okay, so we have all these, I think these are all the technical part of this talk. Next, we I think our life is much easier. So we have this F1 from Q hat to P hat. And then we can state the following main result. Now still we let R be a ring in which P is nilpotent. Then we have a transfer F1 minus ID. So we change this F1 a little bit from Q hat to P hat. Then one can show that this thing is injective and the co-kernel is a formal group. So we get from linear objects to formal groups. Therefore, we obtain a functor denoted by BT from the category of displays over R to the category of formal groups over R. And it sits in the following short exact sequence. Moreover, if we restrict BT to the subcategory of nilpotent displays, so we have the definition for nilpotency, and then we restrict to the subcategory, then we obtain an equivalence between the category of nilpotent displays over R and the category of p-divisible formal groups over R. So this is very nice. So one can see that now this R is very general. It can be any ring in which P is nilpotent. Actually, we can then go to limit and assume R is a p-adic ring. And comparing to the Delaunay theory, this is much stronger. and it has many applications, and I think so. It has many applications. On the other hand, a lot of people don't know about this space. And somehow, I would like to advertise these objects, so they are powerful. So, in the rest of this talk, I will show you one example. So, we study some other objects which are special formal groups. So we start with the ring of integers of a finite extensions of QP. We fix the uniformize the pi, and we let R be an O algebra. A formal O module G over R is a formal group G over R. So now we consider formal groups with more symmetries. So this formal group G has an action of O. So we have a morphism iota from this O to endo G. And we require that the action of O on the knee algebra of G induced by this iota is the same as the action induced by this algebra structure. And our goal is to classify pi-divisible formal O modules. Why are these objects interesting? Yeah, so this knee algebra, so this O acts on G, so it induces an action of this O on knee algebra. And on the other hand, this knee algebra is an R module. Yeah, so we have this the second action from this algebra structure. So I think which one is failed? Yeah. Oh, iota is linear, yeah. So there are some examples and applications of these objects. So I think the first important one is given by Drinfeld in 1970s. He generalized Cartier modules and classified formal O modules. And using this classification result, he described p-adic upper half space as the modular space of formal modules. And he went further and proved the p-adic uniformization for Shimura curves over Q. So that's, I think, that's the first p-adic uniformization result I know. And then in 2001, in the famous book of Harris Taylor on local Lorentz correspondence, they use O modules with level structure to construct the expected representations. And then in 2017, Rappaport-Zink reconsidered this Drinfeld modular problem, and they studied the relation with local Shimura data. Roughly speaking, they proposed the conjecture on the modular problem of formal O modules. They confirmed the conjecture in case O is unramified using FO displays with some other objects. And they mentioned in their paper that the general case solved by Scholz with methods from integral p-adic Hodge theory. So since Scholz has thought about this problem, so we change our direction and consider another kind of question. So the modular problem for formal O modules, so with the following conditions.
Runhong think I think the characteristic is connected as some represented by some formal scheme.
Yeah. Yeah.
But I think it shows the fidelity only so it looks like some diamond.
So this sentence may be wrong because I couldn't locate the exact statement of Shaw's, but in their paper of proposed Zink, so they said so they have this sentence. So I don't know. So what's the status of this conjecture? Yeah. Okay, so we consider another kind of question, so which I explain right now. So now let K be an algebraically closed field of characteristic P, and X be a p-divisible group over this K. So everything is easy. And H and D are the height and dimension of X respectively. So the dimension is the same dimension as before, but the height is just this number H satisfies this identity. The order of the P torsion of X is P to the H. Then the following statement holds, so and the proof is not difficult using Dirichlet theory. So it says the following: there exists a minimal number nx such that this x is uniquely determined up to isomorphism by this torsion. I think here xnx, what I mean is x p to the nx, the p to the nx torsion of x. Yeah, this nx depends on x. So there exists a minimal one. Yeah. So if x prime is a p-divisible group over k such that these two have the same torsion, then these two are isomorphic. So from this statement, it is easy to deduce the following one. So there exists a minimal number bx such that x is uniquely determined up to isogeny by this torsion. So if x prime is a p-divisible group over k such that these two have the same torsion, then they are isogenious. For, certainly bx is less or equal to nx. Here we consider isogenious, here we consider isomorphism. Traversal conjecture says the following. So there are now theorems. In 2007, Nicole Vasu proved the following statement. So they have an upper bound for this bx, and this is somehow the best possible upper bound for all x. Well, we have examples where we have identity here. And then in 2013, now Nicole Vasu they proved an upper bound for this nx. Yeah. So the d is the dimension and h is the height. I should make a remark that the traversal original conjecture says that nx is less or equal to this number, and somehow they disproved this conjecture and get a right bound for this nx. Okay, so what's now? What's next? So we ask the following question. So if this x is a pi-divisible O module, so here x is a general p-divisible group. So if we consider p-divisible groups with more symmetries, is there a bet bound for bx or nx? In the following, I will answer this question for bx. Yes, there is one. So what's the statement of our result? Now still we have this K is a perfect field of characteristic P, and we assume that this K is an O algebra, let Q be the size of the residual field of this O, and we let X be a pi-divisible O module over K. So we have the usual height of X. So the height of X is a number H, such that we have this identity. And we define the O height of X to be the number HO, such that this identity holds. Now let E and F be the ramification index and the degree of residual extension of O over ZP. Then a simple counting argument shows that there's a relation between this H and HO. So this H is bigger. Then our theorem says the following. So the first sentence is vacuous. There exists a minimal number Bx such that X is uniquely determined up to isogeny by this torsion. So if it says the following. So if X prime is a pi-divisible O module over K such that these two have the same torsion, then X prime and X are isogenious. And we have an upper bound for this Bx given by HO instead of H. So as one can see, if this extension is non-trivial, then this HO is smaller than H, and this bound is stronger than the bound with H here. And we give this number Bx a name, so we call this number isogeny cutoff. So if we know this torsion XBx, then we know it's isogeny class. So these are objects over field of characteristic P, and somehow one expects that we can do it with Didot theory, but it turns out Didot theory is not sufficient. We need another classification result which generalizes the result of think and Lau. Now let R be an O algebra, so we still assume this nilpotency condition. So we assume pi is nilpotent in R. And we use the ring of ramified weight vectors WOR. And we have this from Bennis and Verschiebung of WOR. And we have this image of the Verschiebung. Then we have a similar definition for O displays. An O display over R is a quadruple PQFF1, where this P is now a finitely generated projective WOR module. And Q is a submodule of P. It's not too small, and FF1 are F linear morphisms such that these two conditions hold. So then you can see the similarity between the definition of O displays and the definition of displays. Yes, and they're basically the same, is that now we have WOR here, and before we just have WR. And everything we have said for displays has a corresponding part for O displays. So we have normal decomposition, we have structure equation, we have this nilpotency condition, we have all these functors, and we have the following classification result. Now let R be an O algebra with pi nilpotent in it. Then we have a map F1 minus ID from Q hat to P hat. This gives us a functor BTO from O displays over R to formal O modules over R. And this it sits in the following short exact sequence. And if we restrict BTO to the subcategory of nilpotent O displays, we obtain an equivalence between the category of nilpotent O displays over R and the category of pi-divisible formal O modules over R. And we can go further, extend this equivalence to get an equivalence between the category of Didot O displays and the category of pi-divisible O modules. So here we have formal O modules, and here we can add some étale part of this thing. O displays. It's basically the same thing I said before. So we have this O display, then we construct this V sharp and the twist of this V sharp, and we define this VM sharp to be this composition, and we require that this thing is 0 for big M. That's the nilpotency condition. Okay, so we have this theorem. So everything is similar as before, but the proof is very different. Somehow, for the proof of the main result of Zinkand's law, we use at least the proof I know use a description of ring of bit vectors by formal power series, and for which we don't have for the ring of ramified bit vectors. So what we do is to adapt Drinfield's idea. So we use some formal induction. We define a new kind of object, so called so we let O prime pi prime be a finite extension of O pi, and now let R be an O prime algebra. Let this P be an O display over R, and we assume that there's an O prime action of this P. So we have this yielder from O prime to end of P. We say this action is strict if the induced action of this yielder on end of P over Q coincides with the action from this algebra structure. So this corresponds to the O prime module definition. So with this definition, we can construct a diagram like this. So we have the category of nilpotent O displays with strict O prime action over R. We have this category nilpotent O prime displays over R. And we have this category pi prime divisible form O prime modules over R. And we have these two functors we construct here, BTO and BTO prime. The thing is that we can construct a functor gamma OO prime from this category to this category. And we can write the construction is very explicit. We can write down the corresponding displays by very explicit formulas. In particular, so when this O prime over O is unramified, we use the so-called FO displays. That's the object Rappaport Zink used in their paper. Okay, so we have this diagram here. If we know BTO is an equivalence, then we use some induction procedure to show that BTO prime is an equivalence. So the hard part is to prove the following statement. This functor here is an equivalence if and only if it is fully faithful. And assume that BTO is an equivalence, then with this result to show BTO prime is an equivalence if and only if, to show this is an equivalence, we just need to show that it is faithful. Now, these things are all faithful by theory of crystals, and we have the base step BTZP is an equivalence proved by Zinkand law. So the formal induction tells us all these BTOs are equivalents of categories. Okay, so why do we need this O displays? Now we still start with this K, a field of characteristic P, and we let X be a pi divisible O module over this K, And now we know there's a corresponding O display for this x, say PQFF1, and we define the a number of x to be the dimension of this quotient. Now, for our purpose, we would like to prove this theorem. So if this for this x here, if this ax is 0, somehow this is trivial. This is the easy part. If this ax is 1, then x is 1 here, then one can see that the dimension of this thing is 1. So if we take a basis of this vector space here, then the Didot module of x has a less basis generated by this basis here. There's only one element here, and it generates the basis of the Didot module of x. And then we can compute the Newton polygon of x while this generates. So if we know the Newton polygon of x, then we know the isogeny class of x. That's how we do it. So the ax greater or equal to 2 case is much harder. So we need the following theorem. So now let K be such a field. For every pi-divisible O module x over K, we can show that there exists a pi-divisible O module frac x over the ring of formal power series, such that the following two properties hold. First is fiber over K is our original x. And secondly, if we go to the algebraic closure of this thing, then it's frac x, the base change of this frac x has the same Newton polygon as x, and the a number of this thing is at most 1. So we have to reduce to the case ax is less or equal to 1. And this is to prove this result, we really need O displays. As we can see that we need to deform our original x to some x over this small k. Okay, so I think this is the most difficult part in the proof, but we prove it just to give the following definition. So now let x be a pi-divisible O module over K. So we know it satisfies this ought condition. It has a very interesting deformation. And then we can define the so-called weak isogeny cutoff of x to be the smallest number, bx tilde, such that the following conditions hold. So first, if x prime is a pi-divisible O module over K, such that this x prime and x have isomorphic torsions, then its Newton polygon is not strictly above the Newton polygon of x. And secondly, there exists a pi-divisible O module frac x over this ring, such that the following properties hold. So, like before, its fiber over K should be the original x, and the generic fiber here has the same Newton polygon as x. And the third condition says that the isogeny cutoff of this deformation is at most bx tilde, and the a number of this deformation is at most 1. So I think this is, this definition is strange, but once we have this weak isogeny cutoff, the proof is easier. So we can prove the bx is less or equal to bx tilde. So the isogeny cutoff is less or equal to the weak isogeny cutoff. And then we have this property here, the Newton polygon relation. We can use somehow a decrease in induction on the Newton polygon argument to show that this bx tilde is less or equal to this number. If we put these two inequalities together, we get bx, the isogeny cutoff is less or equal to this number. and that's how we prove this upper bound for Bx. Yeah, that's all I would like to say. Thank you.
So you studied two modules which where you're always finite extension of the B. Real integers of finite extension, but I will consider like orders in semi-simple algebras like the maximum order in the division of an algebra.
Yeah. So that's indeed that's what they did in their paper. Yeah. So somehow they consider they replace this O by some order from the semi-simple central algebra, and then so if we just have this iota, the modular problem is messy, so you cannot get anything. So they put some constraints like the characteristic polynomial of the elements from this O. And they have some decomposition condition on the tensor product, and then they call them Cauchy condition and Eisenstein condition. So if they conjecture that if we have these two conditions, then we get a bimodular problem, and the modular space should be the up plane or up half space. Yeah, somehow they did they proved this by some Newton stratification argument. So
also the accounting factor is also they put control from polarity and do some property of Newton strata density.
Yeah, so somehow they have a so if so this nx they prove that this nx somehow depends on the Newton point of this x. They have some relation.
Are there similar results when O is the ring of integer in a carrot?
That I don't know.